Hello there and welcome to Life Beyond Seen, a quiet place where curiosity slows its breathing and the world feels a little larger, a little calmer and a little more mysterious than it did a moment ago. Wherever you happen to be listening from, whether it's late at night with the lights low, early morning before the day properly begins, or somewhere in between where time feels pleasantly uncertain, I'm glad you're here. Tonight, we're turning our attention downward, not toward the past or the stars, but toward a place that exists right beneath us, vast and patient, covering most of our planet while remaining strangely absent from our everyday thoughts, the deep ocean. Not the friendly blue surface that glitters in postcards or laps at holiday beaches, but the abyss below. The part of Earth that begins where sunlight gives up and ends somewhere far beyond the reach of human intuition. It's easy to forget how little of our own world we've actually seen. We carry maps in our pockets, satellites orbit above us, and images of distant planets arrive on our screens in remarkable detail. And yet, the largest living space on Earth remains mostly unvisited, mostly unseen, and largely unknown. The abyss is not empty. It is not silent. It is not finished revealing itself. Even now, in the age of high-definition cameras and robotic explorers, the deep ocean continues to surprise us with forms of life that seem to belong to another reality entirely. Creatures shaped by pressure, darkness, and time, adapted to conditions that would crush, freeze, or suffocate us in moments. Some of them have been seen only once, some only briefly, and some, almost certainly, have never been seen at all. Before we drift any deeper, take a moment to notice where you are right now. Are you sitting, lying down, perhaps already feeling the weight of the day begin to ease? What time is it where you are? Outside your window, is the world dark and quiet, or just beginning to stir? It's a small question, but fitting, because while we explore places untouched by human presence, we're also anchored very firmly in our own small slice of the planet. If you find this journey soothing, intriguing, or simply a gentle way to unwind, a like or a subscription helps this calm corner reach others who might enjoy a slower look at the strange and unseen. There's no rush, though. The abyss has waited millions of years. It can wait a little longer. When most people imagine the ocean, they picture movement. Waves, tides, shifting light. But the deeper you go, the more those familiar qualities fade away. Below a certain point, the surface world becomes irrelevant. Weather no longer matters. Seasons no longer matter. Day and night cease to exist. In their place is a realm defined almost entirely by absence. No sunlight. Very little heat. Crushing pressure. And yet life persists. Not just barely, but creatively, ingeniously. In ways that challenge what we thought living things required in order to exist at all. The abyss begins, roughly speaking, where sunlight can no longer penetrate. This isn't a sharp boundary, more a gradual dimming, like twilight stretched downward for hundreds of meters. Colours disappear first. Reds fade, then oranges, then yellows, until everything becomes shades of blue and black. Eventually, even blue gives up. Below that depth, there is no natural light whatsoever. Any glow that appears comes from the organisms themselves. Flickers, pulses, slow chemical lanterns ignited inside living bodies. In this darkness, vision changes meaning. Seeing is no longer about colour or distance. It becomes about contrast, motion, and sometimes not seeing at all. What's remarkable is not just that life exists there, but that it does so in abundance. The deep ocean makes up the majority of the habitable volume on Earth. If life were measured not by surface area but by space in which organisms can exist, the abyss would dominate the planet. And yet humans have explored only a tiny fraction of it. We've walked on the moon more times than we've visited the deepest parts of our own seas. That fact alone hints at how inaccessible this environment truly is. The reasons are practical and unforgiving. Water is heavy. Pressure increases rapidly with depth. For every 10 meters you descend, the pressure increases by roughly 1 atmosphere. By the time you reach the depths of the abyss, the force pressing inward on every surface is immense. Steel buckles, glass shatters, electronics fail. Even specialized submersibles operate at the edge of their limits, protected by thick walls and cautious engineering. Human bodies, built for air and gentle gravity, are entirely unsuited to such conditions. We cannot swim there. We cannot dive there. We can only send machines, and even they must tread carefully. Because access is so limited, much of what we know about abyssal life comes in fragments. A brief camera feed, a sample pulled up in a net, a single encounter captured before darkness closes in again. This creates a strange situation where creatures can be known to science but remain almost mythical in practice. Described in technical language, catalogued in databases, and yet never truly familiar. There are species whose entire recorded history consists of one specimen, observed once, decades ago, and never encountered again. Not because they vanished, but because the place they inhabit is simply too vast and too difficult to reach. It's tempting to imagine the abyss as static, unchanging, frozen in time, but it is anything but. Deep ocean currents move slowly but persistently, transporting nutrients and heat across enormous distances. Organic matter drifts down from the surface, a constant snowfall of debris known as marine snow, tiny particles of dead plankton, waste, and fragments of life above, settling gradually into the dark. For many abyssal creatures, this is the primary food source, a slow, unpredictable rain that rewards patience and efficiency. In such an environment, speed is less important than endurance. Energy is precious. Waste is minimized. Bodies evolve not for motion but for survival. Some creatures wait, some drift, some anchor themselves to the seafloor and let food come to them. Others roam vast distances in near-total darkness, guided by senses that have nothing to do with sight as we understand it. Touch, vibration, chemical signals, and faint electrical cues become the language of this world. Communication happens without sound. Encounters occur without warning. Life unfolds at a pace that feels almost geological compared to the frantic rhythms of the surface. And yet, despite all this, the abyss is not isolated. What happens above affects what happens below. Changes in surface temperature alter deep currents, pollution sinks, noise travels. Human activity reaches even here, carried downward by processes that operate far beyond our perception. Plastic fibres have been found in deep-sea trenches. Chemical traces linger where no human has ever stood. The abyss is hidden, but it is not protected. What makes this especially striking is how recent our awareness of abyssal life truly is. For much of human history, the deep ocean was assumed to be lifeless, an empty void beneath the waves, too dark and too cold to support anything at all. This belief persisted well into the 19th century. It seemed logical. Life, after all, appeared to need light, warmth, and familiarity. The idea that complex organisms could thrive in perpetual darkness was difficult to accept. That assumption collapsed the moment explorers began dredging the seafloor and finding living creatures where none were expected. Slowly at first, then with increasing confidence, science was forced to revise its understanding of habitability. The abyss was not dead, it was simply different, profoundly different. And as exploration continued, that difference grew stranger rather than more familiar. Every descent into the deep carries the possibility of encountering something entirely new. Not just a new species, but a new way of being alive. A body plan that defies symmetry. A metabolism based on chemical energy rather than sunlight. A reproductive strategy tuned to scarcity and distance. These are not small variations on surface life. They are solutions to problems humans rarely have to consider. How do you find a mate when encounters are rare and unpredictable? How do you survive when food arrives sporadically and without warning? How do you move, sense, and exist in a world where pressure never relents? Some abyssal creatures solve these problems in ways that seem almost excessive. Enormous mouths paired with slender bodies, designed to take advantage of any opportunity that appears. Extendable jaws, transparent tissues, stomachs that can expand far beyond what seems reasonable. Others solve them quietly. Slow growth, long lifespans, minimal movement, a commitment to waiting rather than chasing. And then there are the lights. Bioluminescence is perhaps the most iconic feature of the deep ocean, and also one of the most misunderstood. These lights are not decorative. They are tools, signals, lures, camouflage, warnings. Some organisms glow to attract prey, others to confuse predators. Some use light to communicate with members of their own species, creating brief flashes in the darkness that carry meaning without sound. In a place where light does not exist naturally, producing it becomes a powerful advantage. Despite all of this knowledge, it's important to recognize how incomplete the picture remains. Estimates suggest that a large percentage of deep-sea species have yet to be described. Some may never be. The abyss is not a single environment, but a collection of many, each with its own conditions and challenges. Trenches, plains, vents and ridges create micro-worlds scattered across the seafloor. Each one is capable of hosting life forms found nowhere else on Earth. So when we say the abyss hides creatures no human has ever seen, this is not speculation for dramatic effect. It is a straightforward conclusion drawn from scale, access and probability. The deep ocean is too large, too complex and too difficult to explore completely. There are corners untouched by cameras, depths unvisited by machines, habitats that have persisted for millions of years without interruption. In those places, life continues on its own terms, indifferent to whether it is observed or named. As we begin to move deeper into this subject, it helps to let go of the idea that exploration always leads to closure. The abyss does not offer neat endings or complete maps. It offers glimpses, hints, partial understanding, and perhaps that is part of its quiet appeal. In a world where so much feels catalogued and explained, there remains a place where mystery is not a failure of knowledge, but a natural state. From here, the surface world recedes. Familiar reference points begin to lose relevance. The ocean above becomes a distant ceiling, and the seafloor stretches outward in all directions, dark and patient. What follows is not a descent marked by drama, but by gradual adjustment to the darkness, to the pressure, to the idea that life does not require our approval or comprehension to continue. And as we drift further into the unseen, the question is no longer whether the abyss hides unknown creatures, but how many ways life has found to exist without ever needing to be seen at all. When people talk about the ocean, they usually mean the part they recognize, the surface that reflects the sky, the waves that break against shorelines, the water that carries boats, swimmers, storms, and sunlight. It feels familiar enough to be comforting, even when it's rough. We give it names like sea, bay, gulf, or channel, and we imagine it as something we understand reasonably well. But that familiar ocean is only a thin skin, a moving boundary between air and something far larger beneath it. And below that boundary exists another ocean entirely, one that does not behave like the one we know, does not look like it, and does not follow the same rules. If the surface ocean is the part shaped by wind, weather, and the daily rhythm of light, then the deeper ocean is shaped by weight. Not metaphorical weight, but literal mass pressing downward, layer upon layer, until water itself becomes a force capable of bending metal and crushing empty space out of existence. This deeper ocean begins surprisingly close to the surface. Long before you reach the abyss, long before the word deep feels dramatic, the environment has already changed in ways most people never think about. Within the first few hundred meters, sunlight begins to weaken. It doesn't disappear all at once. Instead, it thins, it stretches, it becomes selective. Certain wavelengths vanish faster than others, leaving behind a filtered version of the world that grows bluer and dimmer with every meter of descent. Fish that appear brightly coloured near the surface turn dull and grey, as the light that reveals their colours is stripped away. Reds become invisible, yellows fade, eventually even blue struggles to persist. Below this fading twilight lies a region that is often called the deep ocean, but even that phrase can be misleading. It suggests a single place, when in reality it is a series of layered environments stacked vertically and spread horizontally across the planet. Each layer has its own conditions, its own inhabitants, and its own way of functioning. The ocean beneath the ocean is not one hidden world. It is many, arranged in quiet complexity. As depth increases, temperature drops. Near the surface, warmth from the sun creates variability. Seasons matter. Currents shift with climate. But deeper down, temperature stabilizes into a narrow range, often just above freezing. This cold is not occasional, it is constant, and constancy changes everything. Chemical reactions slow, metabolism adjusts, growth takes longer, lives stretch out over years, decades, sometimes centuries, unfolding at a pace that feels alien to surface time. Pressure, meanwhile, increases relentlessly. It does not fluctuate, it does not offer relief. It is simply there, pressing inward from every direction. Water, unlike air, is dense, and that density adds up quickly. The deeper you go, the more the water above you weighs. By the time you reach the depths where the abyss truly begins, the pressure is so immense that empty spaces cannot exist. Anything hollow collapses unless it is reinforced or filled. Living things adapt by removing air entirely. Bodies become solid, flexible, or fluid-filled. Bones thin. Tissues soften. Structures that would snap at the surface bend and absorb force instead. This is where the ocean truly diverges from our expectations. We tend to think of depth as a vertical measurement, something you go down into. But for the organisms living there, depth is a constant, not a direction. They are not descending or ascending. They are simply existing at a particular pressure, temperature, and level of darkness, and their entire biology is tuned to that precise combination. Move them upward too quickly and their bodies fail. The pressure drops, gases expand, tissues rupture. What is normal for them becomes lethal in minutes. Because of this, the deep ocean remains largely inaccessible not just to humans, but to itself. Many deep-sea species are trapped by their own specialization. They cannot migrate upward. They cannot follow food sources to the surface. They live within narrow vertical bands, sometimes only tens of meters thick, spread across vast horizontal distances. The ocean beneath the ocean is wide rather than tall, stretching across plains and ridges that cover more area than all continents combined. The seafloor itself is not flat, despite how it is often imagined. It rises and falls, splits and folds, marked by mountain ranges, trenches, volcanoes, and fracture zones. Some of the tallest mountains on Earth are underwater. Some of the deepest valleys are hidden beneath kilometers of water. These features shape currents, trap nutrients, and create isolated habitats that evolve in relative separation. A species living along one deep ridge may never encounter a similar species living only a few hundred kilometers away, separated not by distance alone, but by invisible barriers of current and chemistry. One of the most surprising aspects of this hidden ocean is how connected it still is to the surface, despite the distance and darkness. Material from above constantly drifts downward. Dead plankton, fragments of algae, waste from fish, and organic debris from coastal ecosystems all contribute to a slow, continuous fall through the water column. This is not a dramatic cascade. It is more like dust settling in a quiet room, tiny particles spiraling downward, sometimes taking weeks or months to reach the bottom. For deep-sea organisms, this falling material is not background noise. It is the foundation of the food web. Entire communities depend on it. When surface productivity increases, more food eventually arrives below. When surface ecosystems are disrupted, the effects ripple downward long after the cause is forgotten. In this way, The ocean beneath the ocean is both separate from and dependent on the world above. It exists in isolation, but not independence. There are places, however, where the deep ocean breaks this dependency. Locations where energy does not arrive from the surface at all, but emerges from within the Earth itself. These environments, such as hydrothermal vents and cold seeps, are among the most striking examples of how different the deep ocean truly is. Here, life is not powered by sunlight or falling debris, but by chemical reactions driven by heat and geology. Superheated water rich in minerals pours out of cracks in the sea floor. Chemicals mix, reactions occur. And life organizes itself around these invisible processes. In these places, the familiar rules dissolve completely. Organisms do not need light. They do not rely on photosynthesis. Instead, bacteria convert chemical energy into organic matter, forming the base of ecosystems that exist entirely in darkness. Larger animals build their lives around these bacteria, either by feeding on them directly or by forming symbiotic relationships that blur the line between individual and community. These systems are so different from surface ecosystems that their discovery forced scientists to reconsider what life requires to exist at all. Yet even hydrothermal vents are only one piece of the hidden ocean. Vast abyssal plains stretch between features, covered in fine sediment that accumulates at a pace so slow it is measured in millimeters per 1,000 years. In these quiet regions, life is sparse but persistent. Organisms here tend to be small, slow, and efficient. They cannot afford waste. They cannot afford mistakes. Every movement costs energy. Every opportunity matters. What makes the ocean beneath the ocean so difficult to comprehend is that it operates on scales we rarely experience. Distances are enormous. Time is extended. Changes happen gradually, then all at once. A current shift can alter nutrient flow across an entire basin. A single geological event can create a habitat that lasts for millennia. Species may evolve in isolation for millions of years, unseen and unrecorded, their existence written only in the chemistry of their surroundings. From the surface, it is easy to imagine the deep ocean as static, a frozen backdrop beneath the dynamic world above. But this impression is misleading. The deep ocean moves, it circulates, it responds. Massive currents flow slowly but persistently, connecting distant regions through pathways that take centuries to complete a full loop. Water sinking near the poles may not resurface until it has travelled thousands of kilometres, carrying with it dissolved gases, nutrients, and heat. These deep currents help regulate the planet's climate, storing carbon and redistributing energy in ways that are only partially understood. Despite this importance, the deep ocean remains underobserved. Satellites cannot see it. Buoys barely touch it. Most of our instruments are designed for the surface or near-surface environments, where access is easier and data returns are faster. The abyss does not yield information willingly. Every measurement requires effort, planning, and often significant risk to equipment. A single malfunction can end a mission, leaving behind nothing but guesses and extrapolation. This lack of direct observation means that much of what we think we know about the deep ocean is inferred rather than witnessed. Models predict currents. Chemical signatures hint at biological activity. Occasional samples suggest broader patterns. But inference is not the same as familiarity. There are places on the seafloor that have never been photographed. Regions where no human-made object has ever arrived intact. Entire habitats that exist only as anomalies in datasets, waiting for someone to look more closely. The ocean beneath the ocean is also quieter than the surface world, but not silent. Sound travels differently in water, especially at depth. Certain layers act as channels, carrying noises over astonishing distances. A distant earthquake, an underwater landslide, even the low-frequency calls of large animals can propagate across entire ocean basins. For deep-sea organisms, sound may be one of the few ways to sense events beyond immediate contact. Vibrations become information. Pressure changes become signals. And yet, despite this connectivity, much of the deep ocean remains isolated in practical terms. Reproduction is slow. Encounters are rare. Populations are thinly spread across enormous spaces. This isolation shapes evolution in subtle ways. Species may develop extreme adaptations to ensure survival when encounters finally occur. Some merge physically during reproduction. Some produce vast numbers of offspring, hoping that a few will land in suitable conditions. Others rely on chemical cues drifting through the water, messages sent without certainty of receipt. All of this unfolds beyond the reach of sunlight, beyond the rhythms that govern surface life. There are no days or nights here, no seasons marked by light. Time is measured differently, not by clocks or cycles, but by availability. Food arrives, or it does not. Currents shift, or they remain steady. Life responds accordingly, without urgency, without expectation. Perhaps the most unsettling aspect of this hidden ocean is how easily it escapes our mental maps. We think in terms of land masses and coastlines, of political borders and named regions. But the deep ocean ignores these divisions entirely. It flows beneath them. It connects continents without regard for human categories. The same abyssal plain may stretch from one side of an ocean basin to the other, hosting life forms that have never encountered a shoreline, never experienced a wave, never known the sky. When we say there is an ocean beneath the ocean, we think we know this is what we mean. Not simply deeper water, but a fundamentally different realm, governed by different constraints, populated by life that follows different rules. A place where familiarity dissolves and assumptions fail quietly, one by one. As we continue, attention naturally turns toward the darkness itself, toward what happens when light disappears entirely and the ocean becomes something closer to a void than a space. Because once sunlight is gone for good, the environment changes again, and the adaptations of life grow stranger still. There is a point in the ocean where sunlight does not merely fade, but ends. Not gradually, not poetically, but decisively. One moment there is still a trace of brightness, a suggestion of direction, a faint blue hinting at where the surface might be. And then there is nothing. No glow, no gradient, no up or down that can be sensed by sight. From that depth onward, the ocean becomes a place where light, as a natural feature of the environment, no longer exists at all. This absence is not symbolic, it is physical. Photons from the sun simply cannot travel that far through water. They're absorbed, scattered, and extinguished long before reaching the abyss. The result is an environment that has never known daylight. Not once, not for a moment. For millions of years, generation after generation of organisms have lived and died in complete darkness, without ever experiencing sunrise, shadow, or reflection. To a human mind, this is difficult to grasp because light is so fundamental to how we understand space. We navigate by it. We orient ourselves with it. We measure distance, movement, and safety through vision. Remove light, and the world does not just become dark. It becomes undefined. Edges disappear. Depth becomes meaningless. Direction turns into guesswork. In the deep ocean, this is not a temporary condition. It is the default state of reality. Colour, too, loses its meaning. Colour is not an inherent property of objects. It is the result of light interacting with surfaces and being interpreted by eyes. Without light, colour cannot exist in any functional sense. Many deep-sea organisms still possess pigments, but those pigments often serve purposes unrelated to appearance. Some absorb what little stray light might appear, reducing visibility. Others reflect bioluminescent signals in specific ways. But the idea of bright coloration as a visual display largely belongs to the surface world. In fact, many deep-sea creatures appear red when brought to the surface under artificial light. This might seem counterintuitive, But in the deep ocean, red is effectively invisible. The wavelengths that create red light are absorbed first as sunlight descends. A red organism in the abyss is, from the perspective of other deep-sea eyes, almost perfectly black. Camouflage in a world without light does not rely on blending into scenery. It relies on not reflecting anything at all. Sound behaves differently as well. On the surface, sound is chaotic. Waves crash, wind howls, rain strikes water and land. In shallow environments, noise is constant and layered. In the deep ocean, sound becomes something else entirely. Water carries sound efficiently, especially low-frequency vibrations, but there is far less incidental noise. No wind, no surface turbulence, no snapping of ice or rustling of trees. The deep ocean is not silent, but it is quiet in a way that is difficult to imagine. This quiet is punctuated rather than continuous. A distant seismic event, a landslide cascading down a slope miles away, the low-frequency call of a large animal travelling vast distances through sound channels formed by pressure and temperature gradients. When sound occurs, it can travel far, unimpeded by obstacles that would block it near the surface. For organisms living in darkness, these vibrations may be one of the few indicators that something has changed beyond immediate contact. Even so, many deep-sea species do not rely heavily on sound in the way surface animals do. Hearing, as we understand it, often takes a back seat to other senses. Touch becomes more important. Chemical detection becomes critical. The ability to sense minute changes in water pressure, temperature, or electrical fields can mean the difference between finding food and drifting past it unnoticed. In a world without sunlight, colour, or constant sound, information is scarce. Every signal matters. Every stimulus must be interpreted carefully. This scarcity shapes behaviour in profound ways. Movements tend to be slow and deliberate. Sudden bursts of activity are rare and costly. Energy cannot be wasted responding to false alarms. Life in the abyss favours patience over speed, caution over curiosity. Bioluminescence emerges in this environment not as decoration, but as necessity. It is the one reliable way to create light where none exists. Chemical reactions within living tissues produce controlled flashes, glows, or pulses. These lights are tuned to specific wavelengths that travel efficiently through water and are detectable by the eyes of intended viewers. Some organisms emit steady light, others blink rhythmically, some produce brief, startling flashes meant to confuse or deter. What is striking is how precise these displays can be. In the absence of ambient light, even a small glow becomes significant. A faint pulse can be seen from far away. A pattern can convey information about species, size, or intent. In this sense, bioluminescence becomes a language, not a rich, expressive one like human speech, but a functional system of signals shaped by natural selection. At the same time, light can be dangerous. Producing it makes an organism visible in a world where invisibility is often the safest state. Many deep-sea creatures use light sparingly. Some only illuminate when threatened. Others use it to lure prey, creating a false point of interest that draws attention away from the body itself. In some cases, light-producing organs are detachable, sacrificed as distractions while the animal escapes into darkness. Eyes in the deep ocean reflect this strange balance. Some species have enormous eyes relative to their body size, adapted to capture the faintest glimmer of light. Others have reduced eyes, or none at all. In total darkness, vision becomes less useful, and resources are better invested elsewhere. Blindness in the abyss is not a disadvantage, it is an optimization. For organisms that do retain vision, eyes are often tuned not for sharp images but for sensitivity. Detecting motion matters more than detail. Contrast matters more than colour. A slight flicker can signal food, danger, or opportunity. These eyes are not built to admire scenery. They are built to notice change. The absence of sunlight also reshapes daily rhythms. On the surface, life is synchronized to the cycle of day and night. Activity rises and falls with the sun. In the abyss, there is no such cycle. Time is not marked by light. Instead, it is marked by availability. Food arrives or it does not. Currents shift or remain stable. Biological processes continue without external cues, regulated by internal rhythms that may be loosely inherited from surface ancestors, but gradually decouple from any meaningful reference to a day. Some deep-sea organisms still exhibit patterns of activity that correspond indirectly to surface cycles. This is often because food availability is influenced by what happens above. Plankton blooms near the surface eventually lead to increased marine snow sinking downward. In this way, surface time echoes faintly into the deep, not as light, but as delayed nourishment. Life responds not to sunrise, but to consequences. Without sunlight, photosynthesis is impossible. This removes what is on the surface the foundation of nearly all ecosystems. Plants, algae, and photosynthetic bacteria convert light into energy, forming the base of food webs. In the abyss, that entire process is absent. Energy must come from elsewhere, either from organic matter drifting down from above, or from chemical reactions occurring independently of light. This changes the structure of ecosystems fundamentally. Food chains tend to be shorter, energy transfer is limited, biomass is lower. There is less room for inefficiency. Each organism occupies a narrow niche, finely tuned to the resources available. Competition exists, but it is muted by scarcity. Overexploitation would be self-defeating in a place where replacement is slow. Reproduction too is shaped by darkness and distance. Finding a mate in the abyss is not trivial. Individuals may live far apart, encountering others of their species only rarely. This leads to unusual strategies. Some species are hermaphroditic, capable of reproducing with any compatible individual. Others rely on chemical signals released into the water, hoping they drift far enough to be detected. In extreme cases, permanent physical attachment occurs, ensuring reproductive success whenever an encounter finally happens. In a world without sound as constant feedback, without light as a guide, these strategies evolve quietly. There is no spectacle, no display meant to be admired. Everything is functional. Everything is constrained by physics and chemistry rather than aesthetics. The abyss does not reward beauty. It rewards persistence. What humans often find unsettling about this environment is not just its darkness, but its indifference. The deep ocean does not feel hostile in an active sense. It is not aggressive. It does not chase or threaten. It simply does not care. Conditions exist as they are, and life adapts or fails accordingly. There is no room for sentiment, no margin for error, and yet within this indifference there is complexity. Relationships form, systems stabilize, evolution experiments endlessly, testing variations over spans of time that dwarf human history. The absence of sunlight does not lead to simplicity, it leads to specialization, to forms of life that would not make sense anywhere else. When we imagine unknown creatures hiding in the abyss, it is often with a sense of drama, as though something monstrous is waiting just out of view. In reality, what is hidden is more subtle and in many ways more fascinating. Organisms that move slowly, live long and interact minimally. Life that exists not in defiance of darkness but in harmony with it. As exploration continues, every light lowered into the deep becomes a brief intrusion. Cameras illuminate a small circle of seafloor, revealing shapes that have never been seen under any light before. And then the light moves on, and darkness closes in again, unchanged. The world without sunlight, colour or sound does not adjust itself for observation. It does not respond. It remains as it was, patient and vast. And deeper still, beyond even these first impressions of darkness, the environment becomes more extreme, the adaptations more pronounced. Pressure increases further. Food becomes scarcer. encounters become rarer. Which raises a quiet, persistent question. How far can life be pushed before it stops adapting and starts vanishing altogether? Humans rarely visit the deepest places on Earth for reasons that are not mysterious, not dramatic, and not negotiable. The deep ocean does not resist us out of malice or secrecy. It simply operates under conditions that our bodies, our technology, and our instincts were never designed to tolerate for more than brief moments. The farther down you go, the less forgiving those conditions become, until eventually the idea of a human presence shifts from difficult to unreasonable to effectively impossible. At the most basic level, the problem begins with pressure. On land, we live at the bottom of an atmosphere that exerts a steady force on our bodies. We're so accustomed to it that we never notice it. But water is far denser than air, and that density adds weight quickly. Every metre of descent adds more mass above you, more force pressing inward. At depths measured in kilometres rather than metres, that force becomes extreme, not uncomfortable, not dangerous in the abstract, lethal in a way that leaves no room for negotiation. Human bodies are built around air-filled spaces, lungs, sinuses, middle ears. These spaces rely on pressure balance to function. Even at relatively shallow depths, changes in pressure must be carefully managed to avoid injury. Scuba divers ascend slowly to allow gases dissolved in their blood to escape safely. Failure to do so can result in decompression sickness, where gas bubbles form inside tissues and blood vessels. This can cause pain, paralysis, or death, and this risk exists at depths that are insignificant compared to the abyss. As depth increases, pressure increases to levels that human tissues cannot survive under any circumstances. At several kilometres down, the force exerted by the surrounding water would crush an unprotected human body almost instantly. Bones would not shatter dramatically. Organs would not have time to react. The collapse would be immediate and complete. There is no training, equipment, or physiological adaptation that can overcome this. Humans cannot simply become better divers. The environment exceeds the limits of biology itself. To compensate for this, humans rely entirely on machines. Submersibles, remotely operated vehicles, and autonomous probes are the only way we can access the deepest parts of the ocean. These machines must be engineered to withstand enormous pressure, maintain structural integrity, and function reliably in an environment that actively works against them. Every seal, every joint, every cable becomes a potential point of failure. A single flaw can end a mission or destroy the vehicle entirely. Even with modern materials and careful design, building equipment capable of surviving the deep ocean is expensive, complex, and risky. Pressure-resistant hulls must be thick, heavy, and precisely manufactured. Spherical shapes are often used because they distribute force evenly, but this limits internal space and complicates design. Windows, if included at all, must be made of specialized materials many times thicker than ordinary glass. Every additional feature adds weight, cost, and potential failure points. Beyond pressure, temperature presents another challenge. Deep ocean temperatures hover just above freezing. This cold is constant, not seasonal. Electronics behave differently in such conditions. Batteries drain faster, materials contract, lubricants thicken or fail. Systems designed for surface conditions often perform unpredictably at depth. Engineers must account for this, testing components under simulated conditions that are difficult to replicate accurately. Darkness compounds these issues. Without natural light, every observation requires artificial illumination. Lights must be powerful enough to reveal surroundings, yet efficient enough to avoid excessive energy consumption. They must also withstand pressure and function reliably for extended periods. At the same time, artificial light alters the environment being observed. Some organisms flee, others are attracted. Behavior changes. What is seen is not necessarily representative of normal conditions. Navigation is another major obstacle. GPS signals do not penetrate water. Communication with surface vessels relies on sound. which travels slowly and is easily distorted. This makes real-time control difficult. Piloted submersibles must operate with limited feedback. Remotely operated vehicles respond to delayed commands. Autonomous systems must make decisions without direct human input. In all cases, the margin for error is small. The deeper you go, the longer it takes to reach your destination. Descending several kilometers through water is not quick. It can take hours to reach the seafloor. During this time, systems must remain stable. Life support must function perfectly if humans are aboard, and there is no possibility of rescue if something goes wrong. On land, help can arrive. In space, there are contingency protocols. In the deep ocean, failure is final. This reality imposes psychological limits as well. Even trained explorers report the experience of deep-sea descent as unsettling. The gradual loss of light, the sense of isolation, the awareness that nothing outside the vehicle can support human life. For hours at a time, occupants are sealed inside a small space, surrounded by darkness and pressure, dependent on technology for every breath. This is not a casual undertaking. It requires specific temperament, preparation, and acceptance of risk. Because of these constraints, human crewed dives to extreme depths are rare. They are carefully planned, heavily funded, and infrequent. Only a small number of people in history have ever visited the deepest parts of the ocean in person. These visits are not routine exploration. They are singular events, conducted more as demonstrations of capability than as systematic surveys. Most deep-sea exploration therefore relies on unmanned systems. These vehicles can stay down longer, go deeper, and take risks that would be unacceptable with human occupants. Even so, they are not immune to failure. Communication loss, mechanical malfunction, or entanglement can end a mission. Retrieving a disabled vehicle from the abyss is often impossible. Many lie on the seafloor, silent and unreachable, reminders of how unforgiving the environment is. Cost plays a significant role as well. Deep-sea missions require specialized ships, trained crews, custom-built equipment, and extensive logistical support. A single expedition can cost millions of dollars. Funding is limited, and priorities compete. Unlike space exploration, which captures public imagination and national prestige, deep-sea exploration often occurs out of sight and out of mind. The benefits, while significant, are less immediately visible. There is also the question of return on investment. Each dive covers a tiny area relative to the vastness of the seafloor. Even with advanced mapping and imaging, exploration progresses slowly. It is not possible to survey the deep ocean comprehensively within a human lifetime using current methods. Every mission adds pieces to a puzzle that remains overwhelmingly incomplete. Time itself becomes a barrier. Deep-sea ecosystems operate on scales that do not align with human schedules. Processes unfold over decades or centuries. Observations capture moments, not narratives. Long-term monitoring is difficult and expensive. Equipment left on the seafloor must endure harsh conditions for years without maintenance. Many do not. Another factor often overlooked is fragility. While the deep ocean may seem resilient because of its age and scale, many of its ecosystems are highly sensitive to disturbance. A single physical intrusion can leave marks that persist for decades. Tracks left by submersibles have been observed years later, unchanged. Sediment disturbed by exploration settles slowly, altering habitats in subtle but lasting ways. This raises ethical considerations about how often and how aggressively humans should intrude into environments we barely understand. For all these reasons, humans do not roam the abyss the way we roam continents. We do not build structures there. We do not establish permanent presence. Our visits are brief, cautious, and mediated through layers of technology. The deep ocean remains largely beyond our physical reach, not because we lack curiosity, but because the cost of access is extraordinarily high. This rarity of visitation has consequences. It means that much of what exists in the deepest places on Earth remains unobserved. It means that discoveries happen slowly, often by chance. It means that entire ecosystems may exist without ever being directly witnessed by human eyes. When new species are found, they're often known only through images or samples, never through prolonged study. There is a temptation to frame this as a failure of exploration, but it is more accurately a reflection of scale. The deep ocean is not resisting discovery. It is simply vast enough that discovery takes time measured in generations. Humans have existed for a brief moment relative to the age of the ocean. Our technology is younger still. Expecting comprehensive understanding is unrealistic. As technology improves, access will increase incrementally. Materials will become stronger, sensors more sensitive, autonomous systems more capable. But the fundamental challenges will remain. Pressure will not lessen. Darkness will not recede. Distance will not shrink. The deep ocean will always demand respect. This is why the deepest places on Earth remain rarely visited, not because they are forbidden, but because they are indifferent. They do not adapt to us. They do not accommodate our presence. We must adapt to them, and even then, only temporarily. And in that space between curiosity and limitation, something else persists. The certainty that no matter how much we explore, there will always be more beyond reach, more depth, more darkness, more life existing without observation, which brings us closer to the kinds of creatures that inhabit these places, shaped not by human expectation, but by conditions that make our absence inevitable. Pressure is the first rule of the deep ocean, and it is absolute. It does not fluctuate with weather, mood, or season. It does not pause or soften. It is present at all times, pressing inward from every direction, shaping every movement, every structure, every possibility for life. Darkness follows closely behind as the second rule, not as a lack of illumination to be corrected, but as a permanent condition to be accepted. Together, pressure and darkness do not merely influence survival in the deep ocean, they define it. To understand how life survives here, it helps to set aside surface instincts entirely. On land, and even in shallow water, survival is often about speed, strength, and competition. In the abyss, survival is about tolerance, endurance, efficiency, the ability to exist without excess. Pressure ensures that nothing can be fragile in the way surface organisms often are. Darkness ensures that nothing can rely on sight as a primary guide. Every rule that governs life here flows from these two conditions. Pressure increases predictably with depth, but its effects are anything but simple. At extreme depths, pressure reaches hundreds of times what we experience at sea level. This force does not crush selectively. It presses on everything equally, infiltrating tissues, compressing spaces, altering chemical reactions. Any organism that survives here must be built in a way that leaves no room for collapse. Gas-filled cavities are liabilities. Rigid structures become risks. Even proteins, the building blocks of life, behave differently under such conditions. Deep-sea organisms solve this problem not by resisting pressure, but by yielding to it. Their bodies are often soft, flexible, and compressible. Many lack the hard skeletons or rigid shells seen in surface animals. Instead, they rely on cartilage-like structures or loosely organized tissues that can withstand compression without breaking. Where bones exist, they are often thin and lightweight. Where shells exist, they are reinforced in specific ways that distribute force evenly. One of the most important adaptations involves internal chemistry. At high pressure, molecules pack more tightly together. This can disrupt the shape of proteins, interfering with essential biological processes. Deep-sea organisms counter this by producing specialized molecules that stabilize proteins and maintain proper function under pressure. These chemical adjustments are subtle, but crucial. Without them, metabolism would fail. Cell membranes also adapt. Pressure affects how membranes behave, making them more rigid. To compensate, deep-sea organisms alter the composition of fats within their membranes, keeping them flexible enough to function. This microscopic tuning allows cells to communicate, transport nutrients, and maintain balance in an environment that would otherwise freeze these processes into inefficiency. Darkness, meanwhile, rewrites the sensory priorities of survival. In a place where light does not exist, vision becomes optional rather than essential. Some species abandon it entirely. Eyes shrink, lose complexity, or disappear. Neural resources are redirected toward other senses that offer more reliable information. Touch becomes refined. Chemical detection becomes extraordinarily sensitive. Small changes in water composition can signal food, danger, or proximity to another organism. For species that retain vision, eyes evolve not for clarity but for sensitivity. They may be large, tubular, and oriented upward, designed to detect the faintest trace of bioluminescence against a black background. These eyes are not meant to form detailed images. They are meant to notice difference, a flicker, a pulse, a movement where nothing should be moving. Darkness also influences behavior in quieter ways. Movement becomes economical. Many deep-sea animals drift rather than swim, conserving energy by letting currents do the work. When movement is necessary, it is deliberate and measured. Sudden bursts are rare, reserved for moments of opportunity or escape. Chasing prey over long distances is inefficient in a place where calories are scarce and replacements are slow to arrive. Food availability is one of the most unforgiving constraints in the abyss. With no photosynthesis, energy must come from elsewhere. For most deep-sea ecosystems, that means relying on organic material sinking from the surface. This supply is unpredictable and limited. A large meal may arrive suddenly, then nothing substantial for weeks or months. Survival depends on the ability to endure these gaps. As a result, many deep-sea organisms have slow metabolisms. They burn energy gradually. Growth is slow, lifespans are long. Some species may live for decades, even centuries, growing millimetre by millimetre. This is not a sign of inefficiency, it is a strategy. In a world where food is rare, patience becomes a biological advantage. Reproduction follows the same logic. Producing offspring is costly. In the deep ocean, mistakes cannot be easily corrected. Many species reproduce infrequently, investing heavily in each reproductive event. Others produce large numbers of offspring with the understanding that most will not survive. The balance between quantity and quality shifts depending on environment, but the underlying rule remains the same. Waste is dangerous. Pressure and darkness also shape how species interact. Encounters are rare. Populations are spread thin across vast distances. This reduces direct competition but increases the importance of recognition. When two individuals meet, the interaction matters. Whether it is for mating, predation, or avoidance, misinterpretation can be costly. Signals must be clear and reliable even if they are brief. Bioluminescence plays a role here, but so do chemical cues. Many deep-sea organisms release specific compounds into the water that can be detected by others of their species. These signals drift, disperse, and weaken, but they extend the sensory reach beyond immediate contact. In darkness, chemistry becomes a form of communication. Predation in the abyss follows different rules as well. Visual hunting gives way to ambush and detection of subtle disturbances. Some predators wait motionless for long periods, conserving energy until prey comes within reach. Others use lures, mimicking food or signaling falsely to attract curious victims. The absence of light does not eliminate danger. It simply changes its shape. Pressure adds another layer of constraint to predation. Rapid movement generates stress on tissues. Sudden changes in depth can be lethal. Many deep-sea predators hunt within narrow vertical ranges, unwilling or unable to pursue prey far from their pressure zone. This creates invisible boundaries that structure ecosystems just as effectively as physical barriers. Even waste management becomes a survival issue. Producing unnecessary byproducts costs energy and may attract unwanted attention. Many deep-sea organisms are remarkably efficient at recycling internal resources. Nitrogen, carbon, and other elements are reused wherever possible. Excretion is minimized. The deep ocean does not reward abundance, it rewards balance. One of the most striking aspects of survival under pressure and darkness is how little room there is for error. On the surface, organisms can often compensate for mistakes. Food is relatively abundant. Conditions fluctuate but rarely remain extreme indefinitely. In the abyss, conditions are constant and unforgiving. A poorly adapted trait is not inconvenient. It is fatal. And yet, life persists. Not barely, but persistently, filling niches we once thought impossible. This persistence challenges assumptions about what environments are habitable. It suggests that life does not require comfort or familiarity. It requires only stability and time to adapt. Pressure and darkness do not act alone. They interact with temperature, chemistry, and geology, creating a web of constraints that shape every aspect of existence. But they are the foundation. Remove pressure, and the abyss collapses into something else entirely. Remove darkness, and the ecosystem reorganizes around light. Together they define the rules. These rules are not written anywhere. They are enforced quietly, continuously, through physics rather than intention. Organisms that follow them persist, those that do not vanish without record. Over millions of years, this process sculpts forms of life that appear strange to us, but make perfect sense within their environment. As exploration continues, each new discovery reflects these rules back at us. Every unusual body plan, every unexpected behavior, is not an exception, but a consequence. Pressure and darkness are not obstacles to life in the deep ocean. They are the framework within which life operates. And within that framework, evolution has produced solutions so specific, so finely tuned, that some of them look almost unreal when first encountered. Bodies that seem fragile but are perfectly suited to their surroundings. Senses that operate without light. Lives that unfold slowly, quietly, far beyond human awareness, which leads naturally to the creatures themselves. Because once the rules are set, the forms that follow begin to reveal just how inventive survival can be when there is no alternative. In a place where sunlight has never reached and never will, light appears anyway. Not by accident, not as a reflection, and not as a remnant of the surface world, but as something produced deliberately by living bodies. This is one of the most quietly astonishing features of the deep ocean. Where light should not exist, life makes its own. Bioluminescence is not rare in the abyss. It is common. In fact, it may be the dominant form of visual communication in the deep sea. Estimates suggest that the majority of animals living below the sunlit zones are capable of producing light in some form. This immediately tells us something important. In an environment defined by darkness, light is valuable enough that evolution has repeatedly found ways to create it. But this light is nothing like the steady glow of a lamp or the broad illumination of daylight. It is precise, controlled, purposeful. It flickers, pulses, fades, and flashes in patterns shaped by survival rather than beauty. Every glow costs energy, and energy is scarce. Nothing in the abyss glows without a reason. At its most basic level, bioluminescence is a chemical reaction. Inside specialized cells, molecules called luciferins react with oxygen, catalyzed by enzymes known as luciferases. The result is light, produced with remarkable efficiency. Unlike a light bulb, which wastes much of its energy as heat, bioluminescent reactions generate light with very little thermal loss. In the cold, energy-limited environment of the deep ocean, this efficiency matters. The colour of this light is not random. Most deep-sea bioluminescence falls within a narrow range of blue-green wavelengths. This is not because blue-green light is inherently special, but because it travels farthest through seawater. Other wavelengths are absorbed more quickly. Red light, for example, disappears rapidly with depth. By producing blue-green light, organisms maximize the distance over which their signals can be seen. Yet even within this narrow range, variation exists. Some species emit brief, sharp flashes. Others produce slow, steady glows. Some can control intensity, dimming or brightening as needed. A few can even change patterns, creating sequences of light that appear almost intentional. These are not accidents of chemistry. They are behavior shaped by selection. One of the most familiar uses of bioluminescence is predation. In the darkness, finding food is difficult. Many deep-sea predators solve this problem by turning themselves into traps. The most well-known example is the anglerfish, whose modified dorsal spine acts as a glowing lure. The light dangles in front of the fish's mouth, attracting curious prey that mistake it for something edible. When the prey approaches, the distance between interest and death is measured in centimeters. But this strategy is only one variation among many. Some predators emit light from within their mouths, briefly illuminating prey just before capture. Others produce light along their bodies to draw attention away from vital areas, confusing attackers or prey alike. In some cases, light is used to illuminate prey indirectly, causing reflections that reveal movement in an otherwise invisible environment. Prey species, too, use light strategically. One common defense is counter-illumination. Some animals produce light on their undersides that matches the faint glow filtering down from above, effectively erasing their silhouette when viewed from below. This is camouflage not against scenery, but against contrast. In a world where predators look upward for shadows, becoming invisible means becoming luminous. Other species use light as a warning. Sudden flashes can startle predators, creating a moment of confusion that allows escape. Some organisms eject glowing substances into the water, forming luminous clouds that obscure their movement. The light draws attention away from the animal itself, lingering as the real target disappears into darkness. Communication is another critical function. In the deep ocean, finding a member of your own species can be extraordinarily difficult. Populations are sparse, encounters are rare. Bioluminescent signals help bridge this gap. Species-specific patterns allow individuals to recognize one another without direct contact. A particular rhythm or intensity becomes a signature, reducing the risk of wasted energy or dangerous mistakes. In some cases, these signals are used only during specific life stages or behaviors. A species may remain dark for most of its life, illuminating only when searching for a mate. Others glow continuously, maintaining a low-level signal that marks their presence. The diversity of strategies reflects the diversity of challenges faced in the abyss. Not all bioluminescence is produced by the animals themselves. In many deep-sea species, light comes from symbiotic bacteria living within specialized organs. These bacteria generate light continuously, sustained by nutrients provided by the host. The host, in turn, controls when and how the light is visible, often through shutters, lenses, or reflective tissues that direct the glow outward. This relationship adds another layer of complexity. The animal is not just using light, it is maintaining a living light source. This requires balance. The bacteria must be kept alive but not allowed to overwhelm the host. The host must provide resources without wasting them. The result is a partnership refined over evolutionary time, producing reliable illumination in a world that offers none. What makes bioluminescence especially intriguing is how often it has evolved independently. The chemical pathways vary. The structures that house light-producing cells differ, the purposes change, and yet the outcome is the same. Light appears in darkness again and again, suggesting that under these conditions the advantage of light is strong enough to overcome its cost repeatedly. To human observers, these glowing creatures often seem otherworldly. Cameras capture points of light drifting through black water, bodies outlined briefly before vanishing again. It is tempting to interpret these scenes as eerie or dramatic, but for the organisms involved, this is simply how the world works. Light is not a spectacle. It is a tool. cool. There is also an important limitation to remember. Artificial light from human submersibles is vastly brighter than anything produced naturally in the deep ocean. When we illuminate the abyss, we flood it with intensity it was never shaped to handle. Many organisms react strongly, either fleeing or freezing. Some may be injured, others may be drawn in unnaturally, altering their behaviour in ways we do not fully understand. This means that much of what we observe about bioluminescent behaviour is incomplete. We see flashes triggered by disturbance, glows altered by stress, patterns disrupted by intrusion. The natural rhythms of light in the abyss often occur beyond our ability to witness them directly. Even so, each glimpse reinforces the same conclusion. Darkness does not mean emptiness, it means adaptation. Where light is absent, life creates it, not to defy the environment, but to work within it. There are likely countless bioluminescent species yet to be seen. Some may glow in ways we have never observed. Some may use wavelengths outside our detection range. Some may produce light so faint or so brief that our instruments miss it entirely. Given how limited exploration remains, this is not speculation, it is expectation. Bioluminescence also raises questions that extend beyond the ocean. It forces us to reconsider assumptions about life elsewhere. If organisms on Earth can thrive in darkness by generating their own light, what might be possible on other worlds? What forms of communication or perception might arise in environments unlike our own? For now, these questions remain open. What we do know is that in the deep ocean, light is not a given. It is earned. It is shaped by survival pressures so strict that every photon matters. The glow of a deep-sea creature is not decoration. It is evidence of a long evolutionary conversation between chemistry and necessity. As we continue downward, the creatures themselves begin to change even more dramatically. Light may reveal them briefly, but it does not make them familiar. Their bodies stretch, compress, and reorganize around the constraints of their environment in ways that challenge intuition. And as strange as glowing forms may seem, they are only one part of a much larger pattern of adaptation waiting in the darkness ahead. To understand how life persists in the deep ocean, it helps to imagine what would happen if a human body were placed there without protection. There would be no warning period, no gradual adjustment, no sensation of pressure building over time. The force exerted by the surrounding water would be immediate and overwhelming. Any air-filled space would collapse. Tissues would compress beyond their ability to recover. Structural integrity would fail in moments. It would not feel like being crushed in the way we usually imagine. It would feel like the sudden erasure of form. This is the environment in which countless organisms live their entire lives, not briefly, not as an extreme challenge to overcome, but as a stable, everyday condition. Their bodies are not resisting pressure. They are designed around it. Every aspect of their structure reflects the fact that pressure is not an external threat, but a constant presence that cannot be avoided, only accommodated. One of the first differences you notice when observing deep-sea organisms is how soft many of them appear. Compared to surface animals, they often look fragile, gelatinous, or loosely assembled. This impression is misleading. Softness is not weakness in the abyss. It is strength. Rigid structures crack under pressure. Flexible ones yield and survive. Many deep-sea animals lack hard skeletons entirely. Instead, their bodies are supported by water itself. At great depth, internal and external pressures equalize, allowing tissues to maintain shape without the need for rigid support. Muscles and connective tissues provide structure where needed, but nothing is overbuilt. There is no excess material. Everything serves a purpose. Where bones do exist, they are often reduced, thin, lightweight. In some species, bones are replaced by cartilage or other flexible materials that compress without breaking. In others, skeletal elements are present but porous, minimizing density while maintaining function. These designs are not compromises. They are solutions tuned precisely to the environment, Air, which plays a critical role in buoyancy and respiration at the surface, becomes a liability at depth. Gas compresses under pressure, shrinking and destabilizing structures that rely on it. As a result, deep-sea organisms eliminate gas-filled spaces wherever possible. Swim bladders, common in surface fish, are often absent or modified beyond recognition. Buoyancy is achieved through other means, such as lipid-rich tissues that are less compressible than gas. These lipids serve multiple functions. They help maintain buoyancy, provide energy reserves, and remain fluid at low temperatures. In the cold, high-pressure environment of the deep ocean, fats behave differently than they do at the surface. Deep-sea organisms adjust the composition of these fats to prevent them from solidifying, ensuring that tissues remain functional despite the cold. Internal organs are also arranged differently. Without gravity acting in the same way it does at the surface, there is less need for rigid internal positioning. Organs can be loosely packed, suspended within the body cavity, without the need for strong attachments. This reduces stress under pressure and allows the body to absorb compression more evenly. Perhaps the most counterintuitive adaptation is size. Some deep-sea organisms are surprisingly large. This phenomenon, sometimes referred to as deep-sea gigantism, occurs in certain groups where individuals grow far larger than their shallow water relatives. The reasons are still debated, but pressure and temperature likely play a role. Slow metabolism, reduced predation, and extended lifespans allow some species to grow steadily over long periods. At the same time, many deep-sea species are extremely small. Tiny crustaceans, worms, and microorganisms thrive in the sediments and water column, forming the foundation of deep-sea ecosystems. Size, it turns out, is not dictated by pressure alone. It is shaped by energy availability, reproductive strategy, and ecological role. The abyss accommodates extremes, provided they align with the rules. One of the most striking body adaptations involves the ability to withstand sudden changes in pressure, not because the organisms experience them often, but because when they do, the consequences are severe. Many deep-sea species are restricted to narrow depth ranges. Move them upward too quickly, and their bodies cannot adjust. Tissues rupture. Internal chemistry destabilizes. Survival depends on staying within precise pressure boundaries. This specialization creates invisible vertical borders in the ocean. A species may occupy a depth range of only a few hundred meters within a water column that spans several kilometers. These boundaries are not marked by physical barriers, but by physiological limits. Crossing them is not a migration. It is a fatal mistake. Darkness reinforces these constraints. Without light, orientation becomes internal rather than external. Many deep-sea organisms rely on statocysts or similar structures to detect position and movement. These sensory organs provide information about orientation without relying on vision. Others use subtle pressure gradients or current flow to maintain position. Sensory systems overall are reshaped by the environment. Eyes, when present, are often specialized, but touch, chemical detection, and mechanoreception become dominant. Some species possess elongated appendages covered in sensitive receptors, extending their sensory reach far beyond the body. In darkness, contact is information. A faint vibration can reveal prey. A slight chemical trace can signal a nearby organism. Feeding structures reflect scarcity. Many deep-sea predators have disproportionately large mouths relative to their body size. This allows them to consume prey nearly as large as themselves, taking advantage of rare opportunities. Their jaws may be hinged in unusual ways, capable of opening far wider than surface equivalents. Teeth may be long, thin, and angled inward, preventing escape once contact is made. Stomachs, too, are often expandable. A single large meal may need to sustain an organism for weeks or months. Digestive systems are designed to extract maximum energy from whatever arrives. Nothing is wasted. Digestion may be slow, but it is thorough. In contrast, filter feeders in the deep ocean often adopt entirely different body plans. Some anchor themselves to the seafloor, extending feathery structures into the water to capture passing particles. Others drift, spreading delicate nets or mucus sheets that trap organic matter. These structures may look fragile, but they are resilient within their environment, flexing rather than breaking under currents. Reproductive anatomy reveals further adaptation. In a world where encounters are rare, reproductive success cannot rely on chance alone. Some species produce hermaphroditic individuals, ensuring compatibility whenever two members meet. Others evolve extreme sexual dimorphism, where one sex is drastically smaller than the other. In some cases, males attach permanently to females, becoming little more than reproductive organs sustained by the host's body. These arrangements may appear strange or even unsettling to human sensibilities, but they are efficient. They eliminate the uncertainty of finding a mate in a vast, dark environment. Once attachment occurs, reproduction becomes a certainty rather than a gamble. Developmental stages often differ dramatically from adult forms. Many deep-sea species begin life in shallower waters, where food is more abundant. Larvae may drift near the surface before gradually descending as they mature. During this descent, their bodies transform, shedding surface adaptations and developing traits suited for pressure and darkness. This life cycle allows species to exploit multiple environments without requiring adults to migrate. The transition is not trivial. It involves changes in body composition, metabolism, and sensory systems. Some organs regress, others develop. The organism that reaches the abyss is often unrecognizable compared to its juvenile form. This flexibility is another way life navigates the constraints of the deep. Perhaps the most important adaptation of all is stability. Deep-sea environments change slowly. Temperature remains constant. Pressure does not vary. Food supply fluctuates, but patterns persist over long timescales. In response, many deep-sea organisms evolve long lifespans. Growth is slow, reproduction is infrequent, mortality rates are low. There is little advantage to rapid turnover in a place where replacement is uncertain. This longevity affects body maintenance. Repair mechanisms are efficient. Damage accumulates slowly. Some species show little sign of aging in the way surface animals do. Their bodies are built not for speed or intensity, but for endurance. When we bring these organisms to the surface, even briefly, their bodies betray how specific their adaptations are. Without pressure, tissues expand, structures collapse, colours change as light interacts with pigments never meant to be seen. What appears fragile on deck was perfectly stable at depth. The environment, not the organism, is what determines viability. This is why deep-sea creatures often seem unreal in photographs. Their bodies look exaggerated, unfinished or distorted. But these impressions arise from viewing them outside their intended context. In their own world, they are balanced, efficient and complete. The idea that the deep ocean would crush us instantly is not an exaggeration. It is a statement of fact. But the creatures that live there are not defying that force. They are shaped by it, down to the smallest molecular detail. Their bodies are not adaptations layered on top of a surface blueprint. They are fundamentally different designs, evolved under rules that never included human survival. As exploration continues, each new form discovered reinforces the same lesson. Life does not converge on a single optimal shape. It diverges, exploring possibilities constrained only by physics and chemistry. In the abyss, those constraints are severe but not prohibitive. They guide evolution into forms that seem improbable, only because we're not used to thinking beyond our own environment. And still, these are only the forms we have seen. Bodies captured on camera, samples brought to the surface, shapes briefly illuminated before disappearing again. Given how little of the deep ocean has been observed, it is reasonable to assume that many other body plans exist, shaped by the same rules, but expressed in ways we have yet to imagine. Some may be smaller, some larger, some slower, some stranger. All built for a world that would erase us without hesitation, and all thriving quietly in the pressure and darkness that define their existence. As attention shifts from structure to perception, another question begins to emerge. How do these creatures experience their world? What does it mean to sense, to navigate, to understand surroundings when sight is limited or absent altogether? Because survival is not only about having the right body, it is also about interpreting a world that offers almost no familiar cues at all. In the deep ocean, seeing is no longer about looking at things. It is about detecting the slightest hint that something exists at all. Vision, as humans understand it, depends on light bouncing off surfaces and returning to the eye with enough information to form shapes, colours and distance. In a world without sunlight, that entire system collapses, and yet eyes persist. Not always, not everywhere, but often enough to reveal how flexible perception can be when the rules change. Some deep-sea creatures have no eyes at all. This is not a defect or a loss. It is a decision made by evolution. Maintaining eyes costs energy. Building them, wiring them to the brain, processing visual information, all of this requires resources. In total darkness, where light never appears, those resources are better spent elsewhere. For species that live in sediment or in zones where bioluminescence is rare, eyes offer little advantage. Over generations, they shrink, simplify, and eventually disappear. What remains is not blindness in the human sense, but irrelevance. Vision simply stops being useful. Other species take the opposite approach. They develop eyes so large, so sensitive that they seem disproportionate to the body. These eyes are not designed to see landscapes or recognize faces. They are designed to detect contrast, movement, a single photon. In the abyss, the difference between survival and starvation may come down to noticing a faint glow that lasts less than a second. These eyes often look strange to us. Tubular rather than round, oriented upward instead of forward, fixed in place rather than movable. Each of these features serves a purpose. Tubular eyes concentrate incoming light onto a smaller retinal area, increasing sensitivity. Upward orientation allows detection of silhouettes or bioluminescent signals against the faint residual glow filtering down from above. Fixation reduces mechanical complexity, saving energy while maintaining function. Colour vision, as we know it, largely disappears. Colour requires multiple types of photoreceptors tuned to different wavelengths. In the deep ocean, where light is scarce and limited to narrow wavelengths, this complexity offers little benefit. Many deep-sea eyes rely on a single type of photoreceptor, optimized for sensitivity rather than discrimination. The result is a form of vision that is effectively monochromatic, but extremely efficient. And yet, even this simplified vision can be remarkably precise. Some species can detect the polarization of light, an ability that allows them to distinguish between different types of bioluminescent signals. Others can differentiate between wavelengths so subtly that they can tell whether a glow comes from prey, predator, or potential mate. This is not colour vision in the human sense, but it is a form of visual discrimination adapted to the environment. In certain cases, deep-sea organisms possess multiple visual systems. Some have one set of eyes adapted for detecting faint light at a distance, and another for close-range tasks. Others have eyes that change function over the course of their life, adjusting as the organism descends from surface waters into the abyss. Vision is not fixed. It is modular, adaptable, shaped by need. What makes deep-sea vision particularly intriguing is how it balances between seeing almost nothing and seeing everything that matters. In an environment where information is scarce, the visual system cannot afford distraction. It must ignore irrelevant signals and respond decisively to meaningful ones. This leads to highly selective perception. Many deep-sea animals do not see the world as a continuous scene. They see events, a flash, a shadow, a movement. Each one triggers a response. Some species take this selectivity to an extreme. There are fish whose eyes are so sensitive that exposure to bright light can damage them permanently. When submersibles illuminate these animals with artificial lamps, their eyes may be overwhelmed. This is not because the animals are fragile, but because their visual systems are tuned to conditions that humans almost never experience. A light that seems dim to us can be blinding to them. Other species protect themselves by shielding their eyes or keeping them recessed. Some have reflective layers that amplify incoming light, increasing sensitivity without increasing exposure. These layers act like mirrors behind the retina, bouncing light back through photoreceptors a second time. This doubles the chance of detection, a valuable advantage when photons are rare. Then there are creatures whose eyes see something entirely different. Certain deep-sea organisms are sensitive to wavelengths of light that most other species cannot detect. For example, some predators can see faint red light produced by their own bioluminescent organs. Because red light does not travel far in water, this creates a private illumination system. The predator can light up prey without being seen by others. From the prey's perspective, darkness remains complete. This form of hidden vision reveals how perception in the deep ocean is not just about gathering information, but about controlling who has access to it. Seeing and being seen are separate issues. Many adaptations exist to break the connection between the two. In contrast, some species deliberately make themselves visible. They use light to announce presence, deter predators, or coordinate with others. For these animals, vision becomes a social sense, even in a world where social encounters are rare. A brief flash can communicate identity, size, or intent. Eyes tuned to recognize these signals must be precise, able to distinguish between similar patterns in an environment where mistakes are costly. Not all visual information comes from light. In the deep ocean, eyes often work in concert with other senses. Mechanoreceptors detect vibrations. Chemoreceptors detect dissolved compounds. Electrical sensors pick up weak fields generated by muscle movement. Vision provides context, but not completeness. A glow may indicate presence, but vibration reveals direction. Chemistry reveals identity. Together, these inputs form a picture that no single sense could provide alone. This multisensory integration changes how the brain is organized. In many deep-sea species, visual processing centers are reduced relative to surface animals, while other sensory regions expand. The brain is not dominated by sight. It is balanced, efficient, tuned to a world where no single sense can be trusted on its own. The phrase, "eyes that see nothing and everything at once," captures this paradox. On one hand, these eyes see almost nothing by human standards. No colour, no detail, no scenery. On the other hand, they see everything that matters, every meaningful change in the environment, every signal that carries consequence. Vision is stripped of excess and refined to purpose. From a human perspective, this kind of perception is difficult to imagine. We are visual creatures, accustomed to rich, continuous input. Our eyes flood our brains with information, most of which we filter unconsciously. In the deep ocean, the opposite is true. Information arrives rarely, and when it does, it must be processed carefully. There is no background noise to hide mistakes. This difference extends to behavior. Deep-sea animals often remain motionless for long periods, conserving energy and avoiding detection. When something enters their sensory field, the response is immediate and decisive. There is no hesitation, no curiosity. The cost of misinterpretation is too high. It also affects learning and memory. In environments where encounters are infrequent, experiences may be spaced far apart. This suggests that some deep-sea species rely heavily on innate behaviours rather than learned ones. Their responses are hardwired, tested over evolutionary time rather than individual experience. Eyes, in this context, are not tools for exploration. They are triggers for action. One of the most striking implications of deep-sea vision is how it challenges the idea that better vision always means more information. In the abyss, too much information would be useless. There is nothing to fill it with. What matters is sensitivity, not resolution. Detection, not interpretation. The visual systems that evolve under these conditions reflect that reality. As exploration continues, new visual adaptations continue to surprise researchers. Eyes with reflective structures arranged in unfamiliar patterns, retinas with unusual layering, visual pigments tuned to wavelengths once thought irrelevant. Each discovery expands the definition of what an eye can be, and yet, despite all this complexity, much remains unseen. There are likely visual systems that function in ways we do not yet understand, detecting cues we have not learned to measure. Some species may perceive their environment through combinations of light, pressure, and chemistry that defy simple categorization. Our instruments are limited by our assumptions. We look for vision where we expect it, and we may miss it where it operates differently. The deep ocean does not reward assumptions. It rewards precision. Eyes evolve there not as general-purpose tools, but as answers to very specific questions. Is something there? Is it moving? Is it close enough to matter? And once those questions are answered, vision has done its job. Beyond sight, beyond light, beyond the boundaries of what eyes can provide, other forms of life in the abyss push adaptation even further. Some thrive without eyes at all, relying on strategies that bypass perception in favour of chemistry, patience, and timing. Others exist in places where even bioluminescence becomes rare, and survival depends on exploiting the most unlikely sources of energy imaginable. Because in the deepest regions of the ocean, where pressure peaks and darkness becomes absolute, life finds ways to persist that no eye, however sensitive, could fully anticipate. There are places in the deep ocean where the familiar idea of habitat no longer applies. No drifting food from the surface, no gentle accumulation of organic debris, no reliance on what falls from above. Instead, life gathers around cracks in the earth itself, places where the planet's interior leaks into the ocean, releasing heat, minerals and chemicals that would be toxic or lethal almost anywhere else. And here, improbably, life not only survives, but flourishes. These environments sit far below the reach of sunlight, often at depths where pressure is already immense. They are defined not by water alone, but by geology. The seafloor splits, shifts, and vents, allowing superheated fluids to pour into the cold abyss. The contrast is extreme. Water emerging from these openings can be hot enough to melt lead, while the surrounding ocean remains just above freezing. The temperature difference is abrupt, not gradual, creating sharp boundaries where conditions change over distances measured in centimetres. For a long time, it was assumed that nothing complex could live here. Heat that intense, chemicals that corrosive, pressure that high. The combination seemed incompatible with life as it was understood, and yet when these environments were first explored, they were found to be crowded. Dense clusters of organisms arranged around the vents like communities built around a fire in a frozen wilderness. What makes this possible is a complete departure from the energy systems that dominate the surface world. Here, life does not depend on sunlight. It depends on chemistry. Specifically, it depends on the ability to extract energy from compounds such as hydrogen sulfide, methane, and other substances released from the Earth's crust. These chemicals, poisonous to most surface life, become fuel in the deep. At the foundation of these ecosystems are microorganisms that perform a process known as chemosynthesis. Instead of using light to build organic molecules, they use chemical reactions. Hydrogen sulfide reacts with oxygen or nitrate, releasing energy that bacteria use to convert carbon dioxide into sugars and other building blocks of life. In effect, these microbes replace plants as the primary producers of the ecosystem. This is not a marginal process. It is robust enough to support large, complex organisms. Entire food webs are built on this chemical foundation. Animals gather not because food drifts in from elsewhere, but because energy is being generated locally, continuously. as long as the vent remains active. Many of the larger organisms living here form intimate relationships with these bacteria. Some host them inside their bodies, in specialized organs designed to house and nourish microbial partners. In return, the bacteria provide nutrients, effectively feeding their host from within. The line between organism and ecosystem blurs. Survival becomes a shared enterprise. These symbiotic arrangements allow animals to live without mouths, without digestive tracts, without any need to hunt or filter food in the traditional sense. Their bodies become living reactors, managing chemical inputs and outputs with remarkable precision. Blood chemistry adapts to transport toxic compounds safely. Proteins bind substances that would otherwise disrupt biological function. Everything is tuned to maintain balance in an environment where imbalance is the norm. Heat, which destroys proteins and disrupts membranes in most organisms, is accommodated through molecular stability. Proteins in vent-dwelling species are structured to resist unfolding at high temperatures. Cell membranes incorporate lipids that remain intact and functional under conditions that would liquefy or solidify surface equivalents. Enzymes operate efficiently across temperature gradients that would shut down most biological systems. The proximity to vents also means proximity to danger. Conditions change rapidly. A vent can shut down, cutting off the chemical energy supply. New vents can open nearby, releasing fluids that are too hot or too toxic to tolerate. Organisms must respond to these shifts or perish. Some species are highly mobile, capable of relocating when conditions deteriorate. Others rely on reproduction and dispersal, sending larvae into the water column to settle elsewhere. Stone itself becomes part of the habitat. Minerals precipitate out of vent fluids as they cool, forming chimneys and towers that grow and collapse over time. These structures provide surfaces for attachment, shelter from currents, and gradients of temperature and chemistry that create microhabitats. Life arranges itself along these gradients, each species occupying a narrow band where conditions are just tolerable. Beyond hydrothermal vents, similar principles apply at cold seeps, where methane and other hydrocarbons seep slowly out of the seafloor. These environments lack extreme heat, but they are rich in chemicals that support chemosynthetic life. Again, bacteria form the base of the ecosystem, converting chemical energy into biomass. Larger organisms congregate around these invisible resources, creating communities in otherwise barren regions of the seafloor. What unites all of these systems is independence from the surface world. They do not rely on sunlight. They do not rely on falling debris. They are powered by the Earth itself. This independence has profound implications. It suggests that life does not require the conditions we often consider essential. It can arise and persist wherever there is a stable source of energy and the chemistry to exploit it. The organisms living in these environments are often highly specialized. Their bodies reflect the narrow conditions they occupy. Move them too far from their preferred temperature or chemical concentration, and they fail. This specialization creates patchy distributions, dense communities clustered around vents and seeps, separated by vast expanses of seafloor where conditions do not support this mode of life. Despite this isolation, these environments are not static. Vents appear and disappear on geological timescales. Seep activity fluctuates. Over time, communities must relocate, adapt, or vanish. This dynamic nature drives evolution, favouring traits that allow rapid colonization and flexible life cycles. Larval stages are particularly important. Many vent and seep species release larvae that drift in the deep ocean currents, sometimes travelling long distances before settling. These larvae must survive without access to the chemical energy sources they will eventually depend on. They carry enough internal reserves to sustain them during this journey, then undergo dramatic transformations once they reach a suitable site. This life cycle links chemically driven ecosystems to the broader deep ocean. Currents connect distant vents, larvae disperse across basins, genetic exchange occurs over surprising distances, Even in isolation, there is connectivity. From a human perspective, these environments feel alien. Heat without fire, energy without light, life built on poison and stone. But to the organisms that live there, these are simply the conditions of existence. Their biology is not heroic or defiant. It is practical. The discovery of these systems forced a re-evaluation of what environments can support life. It also reframed questions about life beyond Earth. If ecosystems can exist in complete darkness, powered by chemical energy from a planet's interior, then similar systems could exist elsewhere, beneath icy shells, within subsurface oceans, in places where sunlight never reaches. But even without looking beyond Earth, these deep-sea environments remain largely unexplored. Many vents and seeps have never been visited. Others have been observed only briefly. Their communities change over time, responding to shifts we barely monitor. Entire ecosystems may appear and disappear without ever being recorded. This impermanence adds urgency to exploration, but also humility. The deep ocean does not offer stable reference points. It evolves slowly, then suddenly. What is present today may not be present tomorrow, at least on geological timescales. Our observations are snapshots, not histories. Life that thrives on heat, poison, and stone does so because it has no alternative. The rules of survival here are strict. Chemistry replaces sunlight, symbiosis replaces independence, stability replaces abundance. These systems are not anomalies, they are expressions of the same principle seen throughout the abyss. Life adapts to what is available, not to what is familiar. As attention moves away from these chemically fueled strongholds, another kind of mystery emerges. Not life anchored to vents or seeps, but life encountered briefly, unexpectedly, and sometimes only once. Creatures that do not form communities, that do not cluster around obvious resources, and that seem to pass through the abyss like fleeting apparitions. Because beyond the places where life gathers, there are vast regions where encounters are rare, and when they happen, they may never be repeated. There are moments in deep-sea exploration that never quite resolve themselves into understanding. A camera descends, lights cut through the darkness, and something passes through the frame that does not appear again. It is not captured, not sampled, not followed. It appears briefly, moves out of view, and is gone. No second sighting, no confirmation, just footage, notes, and a question that lingers long after the expedition ends. These are not stories of monsters or exaggeration. They are records, logged observations made by trained scientists and engineers, people accustomed to caution and restraint. In many cases, the encounter lasts only seconds. In some, just a single frame. Enough to know that something was there, but not enough to know what it was. The deep ocean makes this kind of encounter inevitable. The scale alone guarantees it. The abyss covers vast areas of the planet, most of which have never been observed directly. Even in regions that have been visited, exploration is sparse. A submersible might traverse a few kilometers of seafloor during a dive that took years to plan. That path is a thread pulled briefly through an ocean-sized fabric. The odds of encountering the same individual or even the same species twice are low. Many deep-sea organisms are not abundant. They do not exist in dense populations. They are spread thinly across enormous spaces, their presence defined more by probability than proximity. Some may exist in numbers so small that encountering one at all is unlikely. Others may be common within a specific niche, but that niche itself is rarely visited. When a creature is seen only once, it occupies a strange position in scientific knowledge. It is not hypothetical, it was observed, and yet it resists classification. Without a specimen, without repeated sightings, it cannot be fully described. It may receive a provisional label, it may be referenced in reports, but it remains, in a sense, incomplete. This incompleteness is not due to negligence. It is a consequence of environment. Collecting specimens at extreme depth is difficult and often destructive. Nets can damage fragile bodies. Suction samplers are limited. Attempting to capture a fast-moving or delicate organism risks losing it entirely. In many cases, the safest option is observation alone, even if that observation is fleeting. Some of these one-time encounters involve organisms that appear almost familiar at first glance. A fish with an unusual body shape, a jelly-like form drifting past the camera, something that resembles known groups but differs in subtle, unsettling ways, extra appendages, unexpected proportions, movements that do not match expectation. Others are harder to place. They do not fit neatly into existing categories. Their bodies may lack obvious symmetry. Their movement may be slow, deliberate, or entirely passive. They may appear to be assembled from elements seen elsewhere, but combined in ways that do not align with known patterns. In the absence of follow-up, these sightings become questions rather than answers. Did the organism represent a new species, or a rare developmental stage of a known one? Was it healthy, injured, or dying? Was it common in that region, or an anomaly passing through? Without repetition, these questions remain unresolved. The deep ocean does not offer easy opportunities for repetition. Conditions vary subtly across space. Currents shift. Food availability changes. An organism encountered once may not be there again, even if the same location is revisited. Time itself becomes a variable. Some species may migrate vertically or horizontally in ways we do not fully understand. Others may have life cycles that bring them into view only briefly. There are also technological limits. Cameras capture only what passes within a narrow field of view. Lights illuminate a small volume of water. Sensors record specific parameters but miss others. An encounter depends not only on the presence of an organism, but on alignment, the right place, the right time, the right angle. Because of this, the deep ocean contains a growing archive of partial encounters, video clips marked with timestamps and coordinates, descriptions that begin with phrases like unknown organism or unidentified gelatinous form. These records are not dismissed. They are catalogued, compared, revisited as new discoveries provide context. Sometimes, years later, a second sighting reveals that a once mysterious organism belongs to a known group. Other times, it deepens the mystery. There are cases where a species is formally described based on a single specimen, collected once and never seen again. This is not uncommon in deep-sea biology. The description becomes a snapshot, frozen in time. It defines a species not as a living population, but as a moment. The organism exists in scientific literature but not in observation. This raises uncomfortable questions. How many species exist in the deep ocean that we have seen once, or not at all? How many have gone extinct without ever being recorded? The abyss operates on timescales that do not align with human observation. A species may persist for millions of years, then vanish due to subtle environmental changes, leaving no trace we can detect. One-time encounters also challenge assumptions about rarity. An organism seen only once is not necessarily rare in its own context. It may be abundant in a region we have never explored. Its apparent rarity may be an artifact of our limited access rather than its actual distribution. In this way, human knowledge is skewed not by the ocean's secrets, but by our own constraints. There is also the issue of fragility. Many deep-sea organisms are delicate. Gelatinous forms in particular do not preserve well. When brought to the surface, pressure changes destroy their structure. Even careful handling can reduce them to unrecognizable fragments. This makes physical study difficult and increases reliance on visual documentation. Visual documentation, however, has its own limitations. Cameras flatten depth. Lighting alters appearance. Movement is captured from a single perspective. Important details may be missed. A structure that appears to be a fin may be something else entirely. Without the ability to examine the organism from multiple angles or over time, interpretation remains tentative. In some cases, these encounters spark debate. Scientists compare footage, propose hypotheses, and argue over classification. Is it a larval form or an adult? A deformity or a distinct species? A known organism behaving unusually, or something genuinely new? Without additional data, consensus is difficult. The public often becomes aware of these encounters through brief clips shared widely, sometimes accompanied by speculation or sensationalism. This can obscure the reality of scientific uncertainty. The truth is less dramatic but more interesting. The deep ocean is not hiding secrets out of intent. It is simply vast enough that partial knowledge is the norm. For researchers, these one-time encounters are both frustrating and motivating. They represent gaps in understanding, but also opportunities. Each unexplained sighting suggests that there is more to learn, more to explore. It reinforces the idea that the deep ocean is not a closed book, but an ongoing investigation. There is also humility in these moments. Seeing something once and not again is a reminder that observation does not equal ownership. The organism does not exist for our benefit or curiosity. It lives its life according to its own constraints and rhythms, indifferent to whether it is documented. Some encounters occur at the edges of technology's reach. A remotely operated vehicle reaches maximum depth. A camera's battery runs low. A submersible must begin its ascent, and just as conditions force retreat, something appears. The timing is unfortunate, but revealing. It suggests that the deep ocean does not arrange itself around human schedules. There are also regions that have been explored repeatedly, yet continue to produce new sightings. This indicates not just spatial vastness, but ecological complexity. Even familiar areas can harbour organisms that evade detection, either through behaviour, camouflage, or sheer improbability. Encounters seen only once also complicate conservation efforts. Protecting what we cannot reliably observe is difficult. Assessing population health or vulnerability becomes nearly impossible. The deep ocean faces increasing pressures from human activity, including mining, pollution, and climate-driven changes. Species we barely know may be affected before we have a chance to understand them. This uncertainty does not invalidate concern, it amplifies it. The fact that so much remains unseen means that impacts may extend beyond what is immediately measurable. The deep ocean's resilience is often assumed, but resilience does not imply invulnerability. From a broader perspective, these fleeting encounters challenge the narrative of exploration as progress toward completeness. The abyss resists closure. Each answer leads to new questions. Each discovery opens further gaps. Knowledge expands, but so does awareness of how much remains unknown. There is a tendency to think of science as a process of accumulation, steadily filling in blanks. In the deep ocean, science often feels like tracing outlines in the dark. Each observation illuminates a small area, leaving the rest unchanged. The illuminated areas do not connect neatly. They form islands of understanding separated by vast unknowns. This does not mean the effort is futile. It means the goal must be adjusted. Understanding the deep ocean is not about cataloguing everything that exists. It is about recognizing patterns, constraints, and possibilities. One-time encounters contribute to this by expanding the range of what is considered possible. They also serve as reminders that the deep ocean is not static. It is dynamic, evolving, and responsive. New species arise, others adapt or disappear. Our glimpses are moments in this ongoing process, not definitive records. When a being is seen only once, it leaves behind more than footage. It leaves behind a trace of humility, a recognition that the world is larger than our frameworks, that life can exist in forms and places we have barely begun to imagine. As exploration continues, some of these one-time encounters may eventually be resolved. A second sighting, a captured specimen, a clearer image. Others may remain singular forever, their existence known only through a brief intersection with human technology. And beyond these isolated sightings lies another layer of mystery. Not creatures that appear and vanish unpredictably, but signals without bodies, sounds without sources, movements without visible cause, indications that something is present, communicating or passing through, without ever revealing its form. Because in the abyss, not everything announces itself through sight alone. In the deep ocean, information does not announce itself clearly. It arrives indirectly, fragmented, often without an obvious source. Where light is absent or unreliable, and where encounters are rare, the environment communicates in other ways. Through sound that travels farther than sight ever could. Through shadows that flicker without revealing shape. Through signals that suggest presence without offering certainty. For humans, this can be deeply unsettling. We're accustomed to environments that explain themselves visually. We expect causes to be visible, sources to be identifiable. In the abyss, that expectation fails. Something can be near without being seen. Something can pass through without leaving a trace. The ocean becomes a place where awareness is shaped by hints rather than confirmation. Sound is the most far-reaching of these hints. Water carries sound efficiently, especially at low frequencies. Unlike light, which is quickly absorbed, sound waves can travel thousands of kilometers through the deep ocean with surprisingly little loss of energy. This creates an environment where distant events can be detected long before or long after their source is nearby. There is a layer in the ocean known as the deep sound channel, formed by the interaction of pressure, temperature, and density. Within this channel, sound becomes trapped, bending back toward the center rather than dispersing upward or downward. The result is a natural acoustic highway, allowing noises to propagate across entire ocean basins. A sound produced in one location may be detected far away, detached from its origin by time and distance. For deep-sea organisms, this means that sound can function as an early warning system, a navigation aid, or a means of communication. Vibrations from a distant landslide, the low-frequency movement of a large animal, the subtle hum of geological activity. These cues provide context in a world where visual confirmation may never arrive. Not all sounds in the abyss are biological. The ocean floor is geologically active. Tectonic plates shift. Volcanoes erupt. Sediment slides down slopes in slow-motion avalanches. These events produce acoustic signatures that ripple through the water column. To an organism living nearby, these sounds are part of the background, not extraordinary occurrences, but regular features of the environment. Some species appear to be sensitive to these cues in ways we do not fully understand. They may adjust behavior in response to changes in ambient sound, moving away from areas of instability or toward newly formed habitats. Sound becomes a map, not of space, but of change. Biological sounds are harder to interpret. Many deep-sea animals do not produce sound deliberately in the way surface animals do. There are no choruses, no constant calls, but movement itself generates vibration. The displacement of water, the contraction of muscle, the snap of a feeding mechanism. These sounds are subtle, but in an otherwise quiet environment, they can be significant. Large animals in particular create acoustic footprints simply by existing. Their mass displaces water. Their movements propagate low-frequency waves that travel far. Even without vocalization, presence can be announced. This may explain why some deep-sea species remain motionless for long periods, minimizing noise as much as conserving energy. There are also indications that some deep-sea organisms do produce sound intentionally, though evidence is limited. Certain crustaceans snap appendages. Some fish may generate vibrations through specialized muscles or structures. These sounds are not well studied, in part because detecting them is difficult. Instruments designed to capture low-frequency noise often cannot distinguish between biological and geological sources without extensive analysis. For human explorers, the acoustic environment of the deep ocean can be confusing. Hydrophones record a constant mixture of sounds: distant shipping noise carried downward, seismic activity, ice movement near the poles, and unexplained signals that resist easy classification. Some sounds repeat, others appear once and never again. These unexplained signals often attract attention. A rhythmic pattern detected briefly, then lost. A low-frequency hum with no clear source. A sharp, transient noise that does not match known phenomena. Most of these eventually receive plausible explanations as more data accumulates. Some do not. It is important to understand that the deep ocean amplifies ambiguity. Distance distorts perception. Time delays obscure cause and effect. A sound detected now may have originated far away, long ago. Without precise localization, interpretation remains uncertain. The abyss encourages caution, not conclusions. Shadows add another layer of uncertainty. Even in darkness, shadows exist, created by artificial light or bioluminescent flashes. A submersible's lamps illuminate a narrow cone, leaving everything beyond in blackness. When something passes through that light, it may appear only as a silhouette. No detail, no texture, just motion. These shadows can be misleading. A small organism close to the camera can appear large. A distant object can seem to move faster or slower than it actually is. Perspective collapses without reference points. What looks like a single large body may be a group of smaller ones moving together. What looks like intentional movement may be passive drifting caught in a current. And yet, shadows matter. They indicate interaction. Something responded to light. Something crossed a boundary. For deep-sea organisms, artificial light is an anomaly. Some flee immediately, others approach. Some remain still, relying on camouflage. The shadow tells us that something is there, even if it refuses to explain itself. Bioluminescent signals complicate this further. A flash appears, then vanishes. Was it a warning? A lure? A reflexive response to disturbance? Without repeated observation, interpretation remains speculative. Patterns that might mean something to other deep-sea organisms are lost on us. There are also signals that are not sensory in the traditional sense. Chemical traces drift through the water, forming gradients that convey information over time rather than space. These signals do not announce themselves suddenly, they accumulate. An organism may detect a change in concentration and infer presence without direct contact. This creates awareness without encounter. Electrical signals play a role as well. Muscle movement generates weak electrical fields. Some deep-sea species are sensitive to these fields, allowing them to detect prey or predators in complete darkness. This form of perception bypasses sight and sound entirely. It is silent, invisible, and precise. For humans, detecting such signals requires specialized equipment, and even then, interpretation is challenging. Instruments can measure changes, but translating those changes into behavior or intent is not straightforward. A detected signal may indicate life, but not form, presence, but not identity. This creates a strange asymmetry. The deep ocean is full of signals but few clear messages. Everything hints, nothing explains. The environment communicates, but not in a language we speak fluently. There are moments when these hints converge. A sound is detected. A shadow crosses the camera. A bioluminescent flash appears nearby. Together they suggest an organism interacting with its environment in ways we only partially perceive. These moments feel significant, not because they reveal something clearly, but because they suggest coherence beneath the ambiguity. At the same time, there are long stretches of silence, hours of descent with no notable sound, no movement, no light beyond what the submersible provides. This absence is not empty. It is simply unresponsive. The abyss does not fill space with reassurance. It offers nothing until something happens, and then it offers only enough to confirm that it did. Human psychology struggles with this. We are pattern-seeking creatures. We want continuity, explanation, narrative. The deep ocean resists all three. Signals appear without context. Shadows move without identity. Sounds echo without source. Meaning must be inferred, cautiously, often incorrectly. This has led at times to misinterpretation. Early recordings of unexplained sounds were sometimes attributed to unknown creatures, only to later be identified as ice movement, seismic activity, or distant human noise. Conversely, some biological sounds may have been dismissed as environmental noise, lost in the background. The line between known and unknown remains porous. Each new dataset adds clarity in one area while introducing new questions in another. Improved instruments reveal signals previously undetectable, expanding awareness but also expanding uncertainty. The more sensitive our tools become, the more complex the abyss appears. For deep-sea organisms, this complexity is simply normal. They evolved within it. Their sensory systems are tuned to extract relevant information from a noisy, indirect environment. They do not require certainty. They operate on probability. A signal indicates risk or opportunity. A response follows. Over time, successful responses persist. Humans, by contrast, seek confirmation. We want to see the source, identify it, classify it. The abyss does not accommodate this desire easily. It offers glimpses, not explanations. There is also the matter of scale. Many signals in the deep ocean operate on timescales and distances that feel abstract to us. A chemical gradient may take days to form. A sound may travel for hours before detection. A shadow may represent something that passed nearby long before the camera recorded it. Cause and effect stretch apart. This temporal separation further complicates interpretation. An organism may respond to a signal long after its source has moved on. What we observe is a reaction, not an interaction. Without understanding the timing, we misread the scene. Despite these challenges, signals from the abyss are not meaningless. They provide insight into how life persists in an environment where direct contact is rare. They reveal a world structured by indirect awareness rather than constant interaction. A world where presence is inferred, not confirmed. These signals also suggest that much of deep-sea life exists just beyond our perception. Not hidden deliberately, but operating at thresholds we rarely cross. Our cameras see what passes in front of them. Our hydrophones record what falls within their range. But life does not organize itself around our instruments. This is why the deep ocean continues to feel haunted by possibility rather than populated by certainty. Sounds hint at movement, shadows hint at form, signals hint at intent. Together, they create an impression of activity without visibility, of life unfolding quietly beyond reach. As exploration progresses, these indirect observations accumulate. Patterns emerge. Some signals recur. Some align with known behaviors. Others remain outliers, resisting explanation. Each contributes to a growing sense that the abyss is not empty between encounters, but active in ways that do not announce themselves clearly. And beyond sound, shadow, and signal lies another constraint that shapes all of this. The simple fact that most of the deep ocean has never been visited at all. Vast regions remain untouched by cameras, hydrophones, or sensors of any kind. Whatever signals exist, they pass unnoticed, unrecorded. Which brings the question back to scale. How much of the abyss remains beyond not just our sight, but our awareness entirely? And how many forms of life persist there, sending signals into the dark, never intercepted, never interpreted? Because before we consider what technology might reveal next, it helps to understand just how much of the deep ocean remains unexplored in the first place. The deep ocean remains unexplored not because humans lack curiosity, but because curiosity alone is not enough to overcome scale, distance, and constraint. Exploration, in this context, is not a matter of willpower or ambition. It is a matter of physics, economics, time, and limitation. When all of these factors converge, the result is an environment that resists comprehensive understanding, not through secrecy, but through sheer immensity. The first and most obvious reason is size. The deep ocean covers more than half of the Earth's surface and extends downward for kilometres. If the seafloor were lifted into the air, its area would exceed that of all continents combined. And yet, most exploration efforts cover only tiny fractions of this space. A single expedition may map or observe a region measured in square kilometres, while the unexplored remainder stretches on almost unimaginably. This imbalance creates a distorted sense of progress. Each successful mission feels significant, and it is, but in terms of total coverage, it barely registers. Even after decades of exploration, the percentage of the deep ocean that has been directly observed remains extremely small. Maps exist, but maps are not understanding. They show contours, not communities. Depth, not life. Distance compounds this challenge. Many deep-sea regions are far from shore, requiring long voyages just to reach the starting point of an expedition. Research vessels must travel for days or weeks before deploying any equipment. These vessels are expensive to operate, consuming fuel, time, and personnel resources continuously. Every additional day at sea increases cost and risk. Once on site, exploration proceeds slowly. Descending to great depth takes hours. Each dive must be planned carefully, accounting for weather, currents, and equipment limitations. Unexpected conditions can force cancellation or delay. Even when everything works as intended, the time spent actually observing the seafloor is limited. A submersible may spend a few hours at depth after an entire day devoted to descent and ascent. Technology adds another layer of constraint. Building equipment capable of surviving extreme pressure is difficult and costly. Materials must be tested extensively. Redundancy is essential. Failures are often catastrophic and unrecoverable. When a deep-sea vehicle is lost, it is not easily replaced. Each mission carries the risk of ending not just the dive, but the availability of that equipment entirely. Autonomous and remotely operated vehicles have expanded access, but they come with trade-offs. Autonomous systems must operate without real-time human guidance, making decisions based on pre-programmed parameters. This limits flexibility. Remotely operated vehicles rely on long cables that restrict range and maneuverability. Both systems require constant monitoring and support from surface vessels. Communication itself is a barrier. Radio waves do not travel through water effectively, forcing reliance on acoustic signals that are slow and imprecise. Data transmission is limited. High-resolution video often must be stored on board and reviewed later, delaying analysis. Real-time decision-making is constrained by latency and bandwidth. Even when data is collected successfully, interpretation takes time. Deep-sea imagery often reveals unfamiliar forms. Identifying species requires careful comparison, consultation with specialists, and sometimes genetic analysis of samples that are difficult to obtain. A single dive can generate months or years of analysis work, slowing the pace of discovery. Funding shapes everything. Deep-sea exploration does not fit neatly into commercial models. The return on investment is not immediate or easily monetized. Knowledge gained may be fundamental rather than applied. As a result, funding often depends on government support, academic grants, or private sponsorship. These sources are limited and competitive. Priorities also matter. Exploration competes with monitoring, conservation, and applied research. Resources devoted to understanding climate change impacts, fisheries management, or pollution tracking may reduce funding available for pure exploration. These choices are not wrong, but they influence what remains unseen. There's also a historical component. Much of ocean science developed alongside surface navigation, weather forecasting, and coastal management. The deep ocean was not immediately relevant to human survival or commerce. As a result, exploration lagged behind other scientific fields. Space exploration, for example, advanced rapidly in part because it aligned with geopolitical competition and public imagination. The deep ocean did not receive the same attention. Risk perception plays a role as well. The deep ocean is unforgiving. Accidents can be fatal. Equipment loss is permanent. Rescue is often impossible. These realities discourage frequent human presence and encourage cautious, infrequent missions. Exploration proceeds methodically, not adventurously. Environmental concerns introduce further complexity. The deep ocean is not a blank canvas, it is a living system. Exploration can disturb fragile habitats. Lights, noise, and physical contact can alter behaviour or damage structures that take decades or centuries to recover. Scientists must balance the desire to observe with the responsibility to minimise harm. This caution slows exploration, but is necessary. The goal is not to conquer the deep ocean, but to understand it without erasing what makes it worth understanding. That restraint limits the number of dives, the duration of missions, and the intensity of sampling. Time itself is a limiting factor. Long-term observation is difficult. Deploying instruments that can operate unattended for years is expensive and technically challenging. Retrieving them is not guaranteed. Without continuous monitoring, many processes remain poorly understood. We see snapshots, not movies. The deep ocean also changes slowly in ways that are easy to miss. Biological processes unfold over long timescales. Population shifts may take decades. Geological changes may take centuries. Human observation windows are brief by comparison. Understanding requires patience that does not align well with funding cycles or academic timelines. There is also the challenge of data integration. Information from different expeditions, regions, and instruments must be combined to form coherent pictures. Standards vary. Formats differ. Historical data may be incomplete or incompatible with modern systems. Building comprehensive models takes time and coordination. Despite these challenges, exploration continues. Advances in material science, robotics, and sensing technology gradually expand reach. New vehicles go deeper, stay longer, and collect more data. Mapping improves. Genetic techniques allow identification from trace samples. Each advance reduces some barrier, but none eliminate them all. What remains unexplored is not just space, but possibility. Entire ecosystems may exist that we have not detected because our instruments are not designed to look for them. Life may persist in forms that do not register clearly on cameras or sensors. Chemical signatures may indicate biological activity that we cannot yet interpret. The deep ocean resists exploration not because it is hidden, but because it is vast, complex, and indifferent. It does not respond to attention. It does not reveal itself more readily with effort alone. It requires sustained, careful engagement over timescales longer than human planning typically allows. This reality can feel frustrating, but it also carries meaning. The fact that so much remains unexplored reminds us that the planet is not fully known, that mystery still exists not at the edges of maps but beneath familiar surfaces. The deep ocean is not an anomaly. It is a fundamental part of Earth that we have only begun to understand. And within that unexplored space lies the potential for discovery that reshapes assumptions. New forms of life, new metabolic pathways, new relationships between geology and biology. Each unexplored region holds not just unknown species but unknown principles. This is why the deep remains unexplored. Not because exploration has failed, but because the task is larger than any single generation. Progress occurs incrementally, through patience rather than conquest. As attention turns forward, another question emerges naturally. If exploration is so limited, and if the deep ocean is so vast, What happens when we do manage to look more closely? What does technology reveal in those brief moments when machines peer into the darkness? Because every glimpse we gain is shaped by the tools we use to see, and those tools, while powerful, come with their own limitations and distortions. When humans look into the deep ocean, they do not do so directly. They peer through layers of technology, each one designed to survive conditions that would destroy an unprotected body almost instantly. These tools do not grant continuous access. They offer brief windows, short visits, controlled intrusions into an environment that does not accommodate prolonged presence. The earliest attempts to observe the deep relied on simple methods, weighted lines, dredges dragged blindly across the seafloor, nets hauled up with whatever they happened to catch. These approaches provided the first clues that life existed at depth, but they offered no context. Organisms arrived damaged, mixed together, stripped from their surroundings. The deep ocean was inferred from fragments rather than observed as a living system. Modern technology has changed this, but only partially. Today's deep-sea exploration depends on a small set of highly specialized tools, each with distinct strengths and limitations. Crude submersibles allow direct observation, placing human eyes behind thick windows of acrylic or glass. Remotely operated vehicles extend reach without risking lives. Autonomous vehicles roam independently, collecting data beyond the range of constant control. Crude submersibles are perhaps the most intuitive form of exploration. They descend slowly, carrying one or two people inside a pressure-resistant sphere. From this enclosed space, observers look out through small viewports, illuminated by artificial lights. The experience is immersive but constrained. Visibility is limited. Field of view is narrow. Time at depth is short. Every movement must be deliberate. These vehicles offer something irreplaceable, however. Human perception, the ability to notice subtle patterns, to respond intuitively, to make decisions based on incomplete information. When something unexpected appears, a human observer can linger, adjust position, and prioritize observation in ways that automated systems struggle to replicate. At the same time, crude dives are rare and expensive. Life support systems must function flawlessly. Emergency scenarios must be anticipated. Depth limits are strict. Only a handful of submersibles in the world can reach the deepest parts of the ocean, and even fewer do so regularly. As a result, human presence in the abyss remains exceptional rather than routine. Remotely operated vehicles, or ROVs, extend exploration without putting people at risk. Tethered to surface ships by long cables, they transmit video and data in real time. Operators guide them from control rooms, adjusting course, manipulating robotic arms, and directing cameras. This allows for longer dives and greater flexibility in sampling. ROVs can carry multiple sensors, high-definition cameras, chemical analyzers, temperature probes. They can collect specimens, take measurements, and explore complex terrain. But the tether that connects them to the surface is both a lifeline and a limitation. It restricts movement, creates drag, and limits how far the vehicle can roam. Entanglement is a constant risk. Autonomous underwater vehicles, or AUVs, remove the tether entirely. They operate independently, following pre-programmed routes. This allows them to cover large areas efficiently, mapping seafloor topography or sampling water chemistry over long distances. They are invaluable for broad surveys and repeated measurements. However, autonomy comes at a cost. These vehicles cannot respond dynamically to unexpected discoveries. If something unusual appears outside their planned path, it may go unnoticed. Decision-making is limited by programming. Flexibility is sacrificed for coverage. All of these tools rely on artificial light. Powerful lamps illuminate the darkness, revealing the seafloor and the organisms that inhabit it. But this light is intrusive. It alters behavior. Some animals flee immediately, others are drawn toward it. What is observed is often a response to illumination rather than natural behaviour. Cameras themselves introduce distortion. Wide-angle lenses exaggerate distance. Limited depth of field flattens perspective. Colours appear differently under artificial light, especially in water, where certain wavelengths are absorbed or reflected unpredictably. An organism's true appearance may differ significantly from what the camera captures. Sound-based technologies supplement visual observation. Sonar systems map seafloor contours, detect objects, and identify features beyond the range of light. These systems are essential for navigation and large-scale mapping. They reveal structure without detail, shape without texture. Passive acoustic sensors listen rather than emit, recording sounds that travel through the deep ocean. These instruments capture geological activity, animal movement, and ambient noise. They provide insight into processes that are invisible to cameras, but interpreting acoustic data is complex. Signals overlap. Sources are ambiguous. Context is often missing. Chemical sensors add another layer. They detect dissolved gases, temperature anomalies, and chemical gradients that indicate biological or geological activity. These measurements can reveal active vents, seeps, or microbial processes even when no organisms are visible. In many cases, chemistry provides the first hint that life may be present. Sampling tools attempt to bridge observation and analysis. Suction devices, cores, and collection chambers allow physical specimens to be retrieved. These samples enable genetic analysis, detailed anatomical study, and laboratory experiments. But sampling is inherently selective. Only certain organisms can be collected intact. Fragile forms are often destroyed in the process. Pressure poses a particular challenge for sampling. Many deep-sea organisms cannot survive the transition to the surface. As pressure decreases, tissues expand and structures collapse. Specialized pressure-retaining containers can mitigate this, but they are complex and limited in capacity. Most specimens arrive altered. This means that much of what we learn about deep-sea life comes from brief visual encounters rather than prolonged study. Behaviour is inferred from seconds of footage. Interactions are guessed at rather than observed over time. Technology gives access, but not familiarity. Even data storage becomes an issue. High-resolution video generates enormous volumes of information. Reviewing, cataloguing, and analysing this data takes time. Patterns may be missed. Rare events may go unnoticed. Human attention becomes a limiting factor. Despite these constraints, technology continues to improve. Cameras become more sensitive, requiring less light. Sensors become smaller and more robust. Machine learning tools assist in identifying organisms and patterns. Networks of instruments provide longer-term monitoring. And yet, the fundamental limitation remains. These technologies offer glimpses, not immersion. They allow us to peer into the darkness briefly, but not to stay. Each dive is an interruption rather than a presence. The deep ocean is not waiting to be discovered in full. It reveals itself incrementally, reluctantly, through narrow technological apertures. Every advance widens the view slightly, but never completely. The darkness always extends beyond the edge of the frame. This reality shapes our understanding. What we know is influenced by what our tools can detect. What we do not know remains vast. Entire forms of life may exist beyond the reach of cameras, sonar, or sensors, operating at scales or in ways we have not yet learned to observe. Technology does not eliminate mystery. It refines it. Each clearer image reveals new questions. Each successful dive highlights how much remains unseen. As these tools continue to evolve, they do more than document the deep. They challenge assumptions about life, environment, and exploration itself. They show us that discovery does not always come as a dramatic reveal, but as a gradual accumulation of partial views. And in those partial views, patterns begin to emerge. Patterns that force reconsideration of what life needs to survive, how it adapts, and how flexible it can be when freed from surface constraints. Because some of the most profound discoveries made through these brief technological glimpses do not simply add new species to a list. They change the rules we thought life followed in the first place. For much of human history, the requirements for life seemed obvious: light, warmth, water, and a narrow range of chemical conditions. Life, it was assumed, was fragile, dependent on a delicate balance that could easily be disrupted. These assumptions were not unreasonable. They were based on what we could see around us. Forests, oceans near the surface, grasslands and reefs all followed similar patterns. Energy came from the sun. Food webs began with photosynthesis. Extremes were places life avoided. The deep ocean dismantled that certainty quietly, piece by piece. It did not do so all at once. There was no single discovery that overturned everything we believed. Instead, there was a slow accumulation of evidence, each finding slightly uncomfortable, each one stretching definitions that had once felt solid. Life appeared where it was not supposed to. It persisted where theory said it should fail. And over time, the idea of what life needed began to unravel. One of the first cracks appeared with the realization that sunlight was not essential. The discovery of chemosynthetic ecosystems revealed that life could build entire food webs without any connection to photosynthesis. Energy could come from chemical reactions alone, provided there was a stable source. This was not a marginal exception. These ecosystems supported dense communities, complex interactions, and long-term stability. This forced a fundamental shift. Light was no longer a requirement. It was one option among many. Then came temperature. Surface life operates within a relatively narrow thermal window. Too hot and proteins denature. Too cold and metabolism slows to failure. Yet in the deep ocean, life exists near freezing temperatures and, in certain environments, alongside fluids hot enough to destroy organic material almost instantly. The key was not avoiding heat, but managing gradients. Life positioned itself precisely where conditions were survivable, even if those conditions changed over distances measured in centimeters. This demonstrated that absolute temperature mattered less than stability and adaptation. Life did not need comfort, it needed consistency. Pressure was perhaps the most humbling lesson. The assumption that high pressure was inherently destructive gave way to the realization that pressure is only a problem for organisms not adapted to it. Deep-sea life did not resist pressure, it incorporated it. At the molecular level, biological systems adjusted to function normally under forces that would obliterate surface organisms. Proteins stabilized, membranes adapted, chemistry shifted. Pressure ceased to be a barrier, it became a parameter. Chemical toxicity followed a similar pattern. Substances like hydrogen sulfide, methane, and heavy metals are lethal to most surface life. In the deep ocean, they became resources. Life evolved not just tolerance, but dependence. Organisms incorporated these chemicals into metabolic pathways, turning poisons into fuel. Toxicity, it turned out, was contextual. A substance was only poisonous if biology had not yet found a use for it. This reframing extended to oxygen itself. While many deep-sea organisms rely on oxygen, others operate at levels that would suffocate surface animals. Some environments fluctuate between oxygen-rich and oxygen-poor states, and life persists by adjusting metabolism accordingly. Aerobic respiration is not mandatory. It is one strategy among several. Even time, in a sense, was rewritten. On the surface, life is fast, growth is rapid, turnover is constant. In the abyss, life slows down. Growth may take decades, reproduction may be infrequent, lifespans stretch far beyond surface norms. This showed that life does not require speed or abundance. It can thrive on patience. Each of these discoveries challenged not just specific assumptions, but the underlying framework used to define habitability. The question shifted from "can life exist here?" to what would life need to adapt in order to exist here. This is a subtle but profound change. It places flexibility, not familiarity, at the centre of biological possibility. The implications reached far beyond oceanography. Astrobiology, the study of life beyond Earth, was transformed by deep-sea discoveries. Worlds once dismissed as barren became plausible habitats. Subsurface oceans beneath ice, planets without sunlight, moons warmed by tidal forces rather than stars. The deep ocean became a reference point, a proof that life does not require Earth-like conditions to persist. At the same time, these discoveries complicated conservation and ethics. If life is so adaptable, does that mean it is resilient to disturbance? The answer increasingly appears to be no. Adaptation does not imply invulnerability. Deep-sea organisms are often finely tuned to specific conditions. Change those conditions too quickly, and adaptation cannot keep pace. Stability, not toughness, is what allows life to persist. This realization forces a re-evaluation of human impact. Activities that alter temperature, chemistry, or sediment composition can disrupt systems that took millions of years to develop. The deep ocean may be flexible in evolutionary terms, but it is not flexible on human timescales. Another assumption that fell away was visibility. For centuries, life was equated with what could be seen. Large organisms, obvious movement, distinct forms. The deep ocean revealed a dominance of microbial life operating at scales invisible to the naked eye. These microbes drive global processes cycling carbon, nitrogen, and other elements in ways that affect the entire planet. Life, it turned out, did not need to be conspicuous to be important. As each new environment was explored, the pattern repeated. Wherever there was a stable energy source and sufficient time, life found a way. The specific forms varied. The chemistry shifted. The pace changed. But the underlying principle remained. Life is opportunistic, not fragile. It occupies possibility wherever possibility exists. This does not mean life is inevitable. Many environments remain sterile, but it does mean that the boundaries we once drew were more reflective of our experience than of biological reality. The deep ocean taught us that our perspective was narrow, shaped by a thin layer of the planet rather than its full depth. Perhaps the most unsettling lesson was how much of this rewriting happened without fanfare. There was no single moment when textbooks were discarded en masse. Instead, assumptions eroded quietly. One paper at a time, one expedition at a time, one unexpected observation layered onto another. Today, the question of what life needs is no longer answered with a checklist. It is answered with a process. Given energy, stability, and time, life explores. It experiments. It adapts. The deep ocean is not an exception to this rule. It is one of its clearest expressions. And still, even with these expanded definitions, there is a sense that something remains incomplete. For all the discoveries that have rewritten our understanding, they are based on the fragments we have observed, the creatures we have studied, the environments we have reached. Beyond those lie vast regions still unseen, habitats that may push the limits even further, forms of life that may challenge assumptions we have not yet realized we hold. Because the more the deep ocean teaches us about what life can do, the more it suggests that there are still possibilities waiting beyond our current reach. Possibilities not yet discovered, not yet imagined, and quietly persisting in the darkness, indifferent to whether we ever notice them at all. The possibility that creatures still exist in the deep ocean, unseen and entirely unknown to humans, is not a romantic idea or a speculative indulgence. It is a logical conclusion drawn from scale, probability, and limitation. When an environment is vast beyond easy comprehension, when access to it is rare and brief, and when life has already demonstrated extraordinary flexibility within it, the expectation should not be completeness. It should be absence, gaps, unknowns. The deep ocean is not a marginal habitat. It is the dominant living space on Earth by volume. Most of the planet's habitable area lies beneath the surface, in darkness, under pressure, beyond direct observation. Even conservative estimates suggest that only a small fraction of this space has been explored in any meaningful way. Not mapped in outline, but observed closely. Not passed over by sonar, but illuminated, sampled and studied. From this alone, the conclusion follows naturally. If life exists there at all, and it does, then there must be life we have not seen. What makes this possibility compelling is not just the sheer size of the deep ocean, but the way life is distributed within it. Deep-sea ecosystems are not uniform. They are patchy, structured around gradients of chemistry, temperature, pressure, and food availability. Some regions support dense communities. Others support sparse, slow-moving populations. Many habitats are isolated from one another by distance, current patterns, or physical barriers on the seafloor. Isolation is a powerful engine for diversification. Over long periods, populations separated from one another adapt independently. Small differences accumulate. Body plans diverge. New species emerge, often with highly specialized traits suited to their particular conditions. In the deep ocean, where isolation can persist for millions of years, this process has had ample time to operate, and yet, human observation has intersected with this process only briefly. Our presence is recent, sporadic, and technologically mediated. We have looked into small windows and tried to infer the whole from what we saw there. This method works poorly when the system being studied is both vast and heterogeneous. Many deep-sea species are known from a single specimen or a handful of encounters. This alone suggests that rarity, or at least apparent rarity, is common. But apparent rarity is not the same as true scarcity. An organism may be abundant within a specific niche that humans have never visited. It may occupy depths beyond current technological reach. It may live in regions where currents, sediment or terrain make exploration especially difficult. There are also organisms whose bodies make them hard to detect. Gelatinous forms, nearly transparent, leave little visual signature even under artificial light. Small organisms may pass unnoticed, indistinguishable from particles in the water column. Slow-moving species may blend into the background, registering as part of the environment rather than as discrete entities. Even among organisms large enough to be seen, behavior can reduce detectability. Some species may remain buried in sediment for long periods, emerging only under specific conditions. Others may be active only at certain times, responding to cues we do not yet understand. A brief visit with a camera does not guarantee an encounter. Technology, for all its sophistication, has blind spots. Cameras see what they are pointed at. Sonar detects structure, not biology. Chemical sensors measure what they are designed to measure, not everything that matters. Entire categories of life may operate in ways that do not register clearly on current instruments. This is not speculation without precedent. History provides many examples. Deep-sea ecosystems around hydrothermal vents were unknown until the late 20th century. Entire classes of organisms were discovered only when exploration reached specific environments. Before that, they did not exist in scientific understanding, despite having existed in reality for millions of years. The same pattern continues. New species are still being described regularly from deep-sea samples. New body plans still surprise researchers. New metabolic strategies continue to emerge from genetic analysis. None of this suggests that discovery is nearing completion. There is also the question of size. While popular imagination often gravitates toward the idea of large, dramatic creatures lurking unseen, the reality is likely more subtle. Many undiscovered species are probably small, microbial, inconspicuous. But small does not mean insignificant. Microorganisms drive global processes. They shape chemistry, influence climate, and support larger life forms. Entire ecosystems may hinge on species we have not yet identified. At the same time, it would be unreasonable to rule out larger organisms entirely. The deep ocean contains animals that rival surface species in size. Some grow slowly, live long, and inhabit regions rarely visited. If such species exist in low densities or in isolated habitats, encounters would be rare. The absence of evidence would not be evidence of absence. What complicates this further is the deep ocean's dynamic nature. Environments shift over geological time. Vents open and close. Currents change. Climate influences chemistry even at depth. Species respond by migrating, adapting, or vanishing. New niches appear. Old ones disappear. Life reorganizes continuously. This means that the set of undiscovered species is not static. It changes over time. Some species may exist now that did not exist in the recent past. Others may have existed until recently and are now gone, leaving no trace we have detected. Discovery lags behind reality. Human activity adds another layer of uncertainty. Pollution, warming, acidification, and physical disturbance reach the deep ocean slowly but persistently. Their effects may alter habitats before they are explored. Species may decline or disappear without ever being observed. The unknown is not protected by being unknown. This possibility challenges the way we think about discovery. It suggests that exploration is not just about curiosity, but about timing. There may be windows of opportunity to observe certain forms of life that close quietly if not taken. The deep ocean does not announce these moments. There is also the matter of perception. Humans tend to recognize life when it fits familiar patterns. Organisms that resemble known groups are easier to classify. Those that do not may be overlooked or misinterpreted. An unfamiliar life form might be dismissed as a variant of something known, or as an artifact of imaging, or as an anomaly not worth pursuing. Only later, with additional context, might its significance become clear, but that context depends on further encounters, which may never occur. This introduces a bias toward recognizing life that aligns with existing frameworks and missing what does not. Genetic analysis has begun to reveal how incomplete our picture is. Environmental DNA collected from deep-sea water and sediment often indicates the presence of organisms that have never been observed visually. Genetic signatures appear without corresponding specimens. These signals suggest diversity that remains hidden, not because it is rare, but because it is inaccessible or unfamiliar. Each genetic sequence represents a lineage, a history, a set of adaptations shaped by conditions we may not yet understand. Without physical observation, these lineages remain abstract, but they are no less real. The possibility of undiscovered life also raises questions about categorization. Our taxonomic system is built on observable traits and genetic relationships. But if life exists in forms that challenge these categories, classification becomes difficult. New branches may need to be defined, new criteria established. Discovery may not just add entries to a list, it may require rewriting the list itself. There is a tendency to assume that the most extreme adaptations have already been found, that the deep ocean's strangeness has been catalogued, but this assumption rests on limited evidence. The known extremes were discovered not because they were inevitable, but because exploration happened to intersect with them. The unknown extremes may exist elsewhere, waiting for the same chance intersection, or they may exist in environments we have not yet learned to explore effectively, or they may exist in forms that do not register as extreme by our current measures. Life does not advertise novelty. It does not arrange itself to be impressive. It persists where it can, adapting quietly. Discovery is an accidental byproduct of human presence, not a guarantee. This leads to a broader reflection. The deep ocean may be one of the last places on Earth where the existence of undiscovered complex life is not just possible, but likely. Not because it is magical or mysterious, but because it is large, difficult, and understudied. Accepting this possibility requires comfort with uncertainty. It requires acknowledging that our knowledge of Earth is incomplete in fundamental ways. that there are still neighbours we have not met sharing the planet in places we rarely consider. This does not diminish what we know, it contextualizes it. It reminds us that knowledge grows outward from limited experience, and that absence of observation is not absence of reality. The creatures still waiting to be found may not resemble our expectations. They may not be dramatic or easily categorized. They may not even be visible in the way we expect life to be visible. But they will be shaped by the same principles that shape all deep-sea life: adaptation to pressure, to darkness, to scarcity, to chemistry. They will exist not as curiosities, but as participants in systems that function independently of our awareness. Systems that cycle energy, matter, and information through the deep ocean, contributing to the stability of the planet as a whole. Whether we ever find them is an open question. Discovery depends on technology, funding, timing, and chance. Some may be observed, others may remain unknown indefinitely, but the possibility itself carries weight. It suggests that the story of life on Earth is not complete, that the chapters we have read are fragments of a much larger narrative unfolding quietly beneath the surface, and as that realization settles in, attention naturally turns inward, toward what this vast unknown says about us, about our place in a world that does not revolve around our presence, about the humility required to accept that we are not the central observers of life on this planet, but late arrivals, peering into systems that were thriving long before we noticed them. Because the abyss does more than hide unknown creatures. It reflects something back at us, if we are willing to look. Standing at the edge of the known world has a way of changing how scale feels. The abyss does this without spectacle, without ceremony. It does not confront us directly. It simply exists, vast and indifferent, and in doing so it quietly rearranges our sense of importance. Not through fear, but through proportion. When confronted with something so large, so old, and so indifferent to our presence, the idea of human centrality begins to soften. The deep ocean does not acknowledge us. It does not respond to curiosity, ambition, or neglect in any immediate way. It functioned long before humans evolved the ability to wonder about it, and it will continue long after our current technologies have become obsolete. This continuity is not hostile, it is neutral, and neutrality, when encountered at this scale, can feel unsettling. Much of human thinking is shaped by environments that react to us. Land responds to footsteps, air responds to sound, surface waters respond to movement and light. Cause and effect are immediate. The abyss breaks this pattern. A submersible descends, lights turn on, instruments hum, and the environment barely notices. The darkness remains, the pressure remains. Life continues or retreats without acknowledgement. This lack of response forces a re-evaluation of significance. It becomes difficult to maintain the illusion that observation equals importance. The abyss does not care that it is being studied. It does not become more real because we are looking at it. It simply reveals, briefly, that it was always there. Human history often frames exploration as expansion, a sense of forward movement, of bringing unknown places into the realm of the known. On land, this narrative carried consequences. Landscapes were altered, ecosystems changed, boundaries shifted. The deep ocean resists this narrative. Exploration does not transform it in the same way. Our presence is fleeting. Our impact, while not non-existent, is limited in scope and scale compared to the size of the system itself. This resistance does not make the abyss invulnerable, but it does make it humbling. It reminds us that not everything can be reshaped to fit human narratives. Some systems are too large, too slow, too distributed. They absorb attention without reflecting it back. The sense of smallness that arises here is not just about physical size, it is temporal. The deep ocean has existed in recognizable form for hundreds of millions of years. Its ecosystems evolved through mass extinctions, continental shifts, and climate cycles that predate humanity entirely. Human civilization occupies a thin slice of this timeline. Our presence is recent, brief, and still unfolding. When framed this way, urgency takes on a different shape. Many human concerns are immediate, tied to short-term outcomes and generational horizons. The abyss operates on different clocks. Change happens slowly, then suddenly. Stability persists for long periods, then rearranges itself through geological or chemical shifts. This does not diminish the importance of human actions, but it contextualizes them. It becomes clear that the planet does not exist to support human narratives. Humans exist within planetary systems that operate independently of intention. The deep ocean exemplifies this independence. It cycles nutrients, regulates climate, stores carbon, supports life that never intersects with human experience. These functions occur regardless of whether we understand them. This realization challenges the idea that knowledge equates to control. Understanding the abyss does not grant authority over it. At best, it grants perspective. It allows us to see ourselves as participants rather than managers, observers rather than owners. There is a quiet discomfort in this shift. Human culture often values mastery, the ability to map, categorize, and predict. The abyss resists complete mapping. Categories remain provisional. Predictions remain uncertain. Each answer generates further questions, not because of failure, but because of scale. This discomfort is sometimes mistaken for insignificance in a negative sense, but the smallness revealed by the abyss is not diminishing, it is clarifying. It strips away exaggerated self-importance and replaces it with context. To be small within a vast system is not to be meaningless, it is to be one component among many. In this context, humility becomes practical rather than philosophical. Recognizing limits leads to caution. Caution leads to respect. Respect leads to restraint. The deep ocean teaches this lesson repeatedly, not through instruction, but through constraint. It allows access only briefly. It demands preparation. It punishes overconfidence. There is also a psychological dimension to this smallness. Humans evolved in environments where survival depended on constant awareness of surroundings. The abyss offers no such feedback. There are long stretches of emptiness punctuated by rare events. This creates a sense of isolation unfamiliar to surface experience. Isolation, in turn, alters perception. In the absence of familiar reference points, the mind becomes aware of its own expectations. Fear arises not from what is present, but from what is not visible. Curiosity persists without guarantee of reward. The abyss becomes a mirror, reflecting internal states rather than external narratives. For some, this is uncomfortable. For others, it is grounding. It places human concerns back into proportion. Daily anxieties shrink when measured against systems that operate on planetary scales. This is not dismissal of human experience, but recalibration. The abyss also reveals how limited sensory perception shapes worldview. Humans rely heavily on vision. The deep ocean deprives vision of relevance. This forces reliance on indirect measures, instruments, and inference. It highlights how much of what we consider real is filtered through sensory convenience rather than objective completeness. When vision fails, certainty falters. Without clear images, assumptions become tentative. This fosters a different kind of thinking, one that values probability over certainty, patterns over isolated events, long-term trends over immediate outcomes. These modes of thinking align more closely with how complex systems actually function. The deep ocean teaches that absence of evidence is not evidence of absence. This lesson applies beyond biology. It applies to climate, geology, and even social systems. What is unseen may still exert influence. What is unnoticed may still matter. There is also a lesson in persistence. Life in the abyss persists not through dominance, but through balance. It does not seek expansion. It occupies niches quietly. It adapts incrementally. This stands in contrast to many human systems that prioritize growth and visibility. Observing this persistence invites reflection. It suggests that longevity does not require prominence, that endurance may depend more on integration than on expansion. The abyss functions as a reminder that survival strategies are context-dependent. What works in one environment may fail in another. The idea of smallness also extends to knowledge itself. Every discovery in the deep ocean expands understanding, while simultaneously revealing how much remains unknown. This is not a flaw in science. It is a feature of studying systems larger than the tools used to study them. Accepting this incomplete knowledge requires patience. It requires comfort with provisional answers. The abyss teaches that certainty is rare in complex systems, and that seeking absolute answers may be less productive than refining questions. This has implications for how humans relate to the planet. The assumption that everything can be known, managed, and optimized is challenged by environments that resist comprehensive understanding. The deep ocean is one such environment, but it is not unique. It represents a broader category of systems that operate beyond immediate human comprehension. Recognizing this encourages restraint. It suggests that intervention should be approached cautiously, with awareness of unintended consequences. When systems are not fully understood, humility becomes a safeguard rather than a weakness. There is also an ethical dimension to this lesson. If humans are not central, if our presence is one among many influences, then responsibility shifts. Stewardship replaces ownership. Care replaces control. The abyss does not require protection because it is helpless, but because it is integral to planetary balance. Smallness, in this sense, does not imply powerlessness. It implies responsibility proportionate to influence rather than ambition. Humans may be small relative to the deep ocean, but our actions can still have outsized effects. Recognizing smallness does not absolve responsibility, it sharpens it. The abyss also reframes the idea of discovery. Discovering something does not grant entitlement. Observation does not equate to claim. The deep ocean resists the notion that naming confers ownership. It exists regardless of classification. This perspective alters how progress is defined. Progress becomes understanding rather than acquisition, awareness rather than dominance. The goal shifts from completion to coexistence. There is a quiet comfort in this reframing. It removes the pressure to be central. It allows human experience to be meaningful without being universal. It places humanity within a larger story rather than at its center. The deep ocean does not diminish humanity. It contextualizes it. It shows that meaning does not arise from scale, but from relationship, from how systems interact, rather than how large they are. In recognizing our smallness, there is room for awe without fear, respect without reverence, curiosity without conquest. The abyss does not ask to be understood completely. It simply exists, offering lessons to those willing to accept limits. And perhaps that is its most subtle teaching. That understanding does not require dominance. That knowledge can coexist with uncertainty. That smallness, acknowledged rather than resisted, becomes a source of clarity rather than insignificance. As attention moves toward the final stage of this journey, there is no sense of conclusion, only of perspective shifting once more. The abyss does not provide endings. It provides context, and with that context comes a quiet invitation. Not to solve the deep ocean, not to exhaust its mysteries, but to carry its lessons back toward the surface. To let awareness of scale, time, and limitation inform how we move through a world that is far larger, older, and more intricate than it first appears. Eventually, every descent into the deep ocean ends the same way, Not with resolution, not with certainty, but with ascent. Thrusters turn upward. Lights dim or switch off. Instruments finish recording, and the long movement back toward the surface begins, slow and deliberate, passing again through layers that feel familiar only because they were crossed before. Nothing about this ascent provides answers in the way humans often expect answers to arrive. There is no summary waiting above, no moment where the abyss explains itself. Instead, what rises with the submersible, with the data, with the observers, is a collection of impressions. Images that refuse to settle into categories, measurements that hint at processes still not fully understood, encounters that remain unresolved. As pressure decreases and darkness thins, it becomes clear that leaving the deep ocean does not mean leaving its questions behind. They come along quietly, embedded in memory and uncertainty. One of the most persistent questions concerns absence, not what we saw, but what we did not. The deep ocean is defined as much by what escapes observation as by what briefly enters it. For every organism recorded on camera, how many passed just outside the beam of light? For every sound detected, how many travelled undetected through layers of water our instruments were not tuned to monitor? This absence is not empty. It is active. Life continues whether observed or not. Processes unfold without regard for documentation. The abyss does not wait for confirmation. As ascent continues, familiar sensory cues return. Light strengthens, colour reappears, pressure relaxes its grip. These changes are subtle at first, then unmistakable. The environment begins to feel less alien, more aligned with human perception, and yet the knowledge gained below does not integrate easily with surface expectations. There is a temptation to translate everything encountered into surface terms, to label deep-sea organisms as extreme versions of familiar life, to describe adaptations as deviations rather than as outcomes shaped by entirely different constraints. This temptation fades slowly, replaced by recognition that comparison only goes so far. The deep ocean does not operate as an extension of surface ecosystems. It is not a darker version of the same world. It is its own system with its own logic. Carrying that understanding upward requires adjustment. Another unresolved question concerns continuity. How connected is the deep ocean to the rest of the planet, really? We know that material sinks, that currents move, that chemistry links surface and depth. But the extent of this connection remains uncertain. Small changes above can propagate downward slowly, invisibly, altering conditions long after their origin is forgotten. This delayed interaction complicates understanding. Cause and effect separate across time. A disturbance at the surface today may influence deep ecosystems decades from now. The deep ocean absorbs consequences without immediate reaction, making it difficult to perceive impact until it is well underway. Ascent brings this realization into sharper focus. It becomes apparent that many processes shaping the abyss occur beyond human timescales. Observation windows are short, conclusions are provisional. What seems stable during a single dive may be part of a longer cycle still unfolding. There are also unanswered questions about behaviour. Much of what is known about deep-sea organisms comes from brief encounters under artificial conditions. Lights alter behaviour, noise disrupts patterns, presence itself becomes a variable. How much of what we observe reflects natural activity, and how much reflects response to intrusion? Without long-term, unobtrusive observation, these questions remain open. The abyss does not offer opportunities for easy correction. Returning to the same location does not guarantee the same conditions. Life moves, adapts, responds. Then there are questions of scale. The deep ocean is not a single environment, but a collection of many, layered and dispersed. Trenches, plains, ridges, vents, and seeps each host different conditions. Within these, microhabitats create further variation. Mapping one region provides little insight into another. This fragmentation suggests that the diversity of life in the deep ocean may be far greater than current estimates suggest, not because life is abundant everywhere, but because it is specialized everywhere. Each niche supports organisms tuned to its precise conditions. Ascent does not resolve this, it reinforces it. The deeper one has gone, the clearer it becomes that understanding requires many descents, across many regions, over long periods. No single expedition can provide completeness. There is also the question of resilience. Deep sea life appears stable, persistent, slow to change, but stability can be misleading. Many deep sea organisms are adapted to narrow ranges of temperature, chemistry and pressure. Rapid changes may exceed their capacity to adapt. Human influence, though indirect, may push systems beyond thresholds we do not yet recognize. The abyss absorbs change quietly. Effects may not be obvious until they are widespread. This creates uncertainty not just about what exists now, but about what will persist. As the surface draws nearer, another realization takes shape. Knowledge gained from the deep ocean often feels incomplete, not because it is insufficient, but because the questions it raises do not have simple answers. They are not problems to be solved once, but conditions to be understood over time. The deep ocean does not present itself as a puzzle with a final image. It presents itself as a process, dynamic, layered, responsive in ways that resist simplification. This understanding alters the role of exploration. Instead of seeking closure, exploration becomes a means of refining perspective. Each dive adjusts assumptions. Each discovery reframes previous understanding. Progress is incremental and often sideways rather than forward. As ascent continues, the sensory world of the surface begins to reassert itself. Light fills the water, movement increases, familiar organisms appear. The contrast is striking. After hours in darkness and quiet, the surface ocean feels busy, crowded, almost chaotic. This contrast highlights how unusual human experience truly is. We live in a narrow band of conditions that support visibility, rapid movement, and constant interaction. The deep ocean exists outside this band, reminding us that familiarity is not universality. Questions follow this realization upward. How many other systems on Earth operate beyond our intuitive grasp? How many processes shape the planet without aligning to human perception? The abyss becomes an example rather than an exception. There is also a shift in how discovery is valued. Seeing something once does not resolve it. Recording a species does not complete its story. Understanding requires context, repetition, and patience. The deep ocean rewards none of these quickly. Ascent brings with it the awareness that many of the most important questions are not about what exists, but about how to relate to what exists without full understanding, how to study without overstepping, how to protect without complete knowledge, how to acknowledge significance without control. These questions do not remain in the deep. They surface with the explorers, with the data, with the quiet recognition that some systems cannot be mastered, only approached. There is no clear boundary where the abyss ends and the surface world begins in a conceptual sense. Physically, the transition is gradual. Psychologically, it is more complex. The lessons of the deep do not dissolve with increasing light. They persist, altering how the surface world is perceived. As ascent nears completion, instruments are powered down, data is secured, the environment returns to something recognizable, and yet there is no sense of completion, only of interruption. The deep ocean remains below, unchanged by the brief visit. Unanswered questions remain unanswered not because they are unsolvable, but because they belong to a system that operates beyond immediate resolution. The abyss does not hurry. It does not conclude. It continues. And so, drifting back toward the surface does not feel like leaving a place behind. It feels like carrying a reminder upward, a reminder that the planet is deeper than it appears, that life is more flexible than we once believed. That knowledge grows slowly and unevenly. The deep ocean remains below, still dark, still pressured, still active. Creatures continue their lives without interruption. Signals continue to travel through water. Chemical reactions continue to generate energy. Evolution continues its quiet work. And somewhere in that vastness, there are still forms unobserved, processes unmeasured, relationships unrecognized. They persist not as mysteries waiting to be solved, but as parts of a system that does not require resolution to function. The ascent ends physically, but not conceptually. Questions remain suspended, much like the particles drifting through the water column. They do not settle easily. They move with currents, resurfacing at unexpected moments. And in that suspended state, between knowing and not knowing, between surface and depth, the story of the abyss continues. Not finished, not concluded, simply ongoing,